Have you ever thought about what would happen if a black hole, drifting silently through the galaxy, suddenly slammed into a neutron star? I'm not talking about the stuff you see in sci-fi movies. I'm talking real events, cosmic-level collisions that actually happen out there in the universe. And the craziest part? We might not even know when one's already happened. Somewhere far away, two of the most extreme objects in space might have already collided, creating a ripple through space-time that passed right through you without you ever knowing. But before we continue, subscribe to the channel so you don't miss out on any of these videos. But here's the thing, this isn't some rare cosmic fantasy. Rogue black holes, the ones that just float through the galaxy with no orbit, no attachments, no warning signs, they're real. And neutron stars? They're like ticking time bombs made of crushed atoms and unspeakable pressure. Put them together, and what you get is something scientists are still struggling to understand. What happens when a rogue black hole merges with a neutron star? What kind of explosion do you get? Does it tear apart the star first? Does it suck it in whole? And what does that tell us about the way the universe works? That's what we're getting into right now. And trust me, the deeper we go, the more questions pop up. This story doesn't just end with a black hole eats a neutron star. It gets weirder, scarier, and way more mysterious. So let's start from the very beginning, the space mystery that's unfolding right now, and why it might change everything we know about the universe. First, let's break down what's at play here. You've got rogue black holes. Those are black holes that aren't stuck orbiting a galaxy or a star. They just move. Alone. Some of them were probably kicked out of their galaxies during massive gravitational interactions. Some were formed when massive stars collapsed and didn't settle into a cozy part of the universe. These rogue black holes are invisible. They don't emit light. They don't announce their presence. The only time we even suspect they're there is when they interact with something, like warping light around them or distorting space-time. Now imagine one of these monsters just gliding through space. Nothing around it. Totally silent. And then it crosses paths with a neutron star. A neutron star is the leftover core of a supernova. It's what's left after a massive star dies in a massive explosion. But here's the freaky part, it's insanely dense. Like you could take all the mass of the sun and squeeze it into a ball the size of a city. That's what we're talking about. 1 teaspoon of a neutron star would weigh about 1 billion tons. The surface is solid, the gravity is off the charts, and deep inside? We don't even fully know what's in there. Some scientists think the core of a neutron star might contain a state of matter we've never been able to replicate on Earth, something called quark-gluon plasma. It's like a zoo of fundamental particles crushed into one hyperdense blob. So, when these two objects meet, a black hole and a neutron star, what happens? Well, in most cases, the black hole wins. Obviously. But it's not always that simple. The merger between a rogue black hole and a neutron star can go in a few different ways depending on a few key things. Like how massive is the black hole? How fast is it moving? How dense is the neutron star? What angle do they collide at? These details change the whole picture. Sometimes, if the black hole is small, yes, some are way smaller than others, it might slowly siphon matter off the neutron star over time. Like a silent thief in the night. The neutron star gets eaten, bit by bit, until it finally disappears completely. Other times, if the black hole is big and moving fast, it might just tear the neutron star apart in seconds. And that violent destruction can release a ridiculous amount of energy, more than anything else in the known universe besides the Big Bang itself. Here's where it gets even weirder. When these two things merge, they send out gravitational waves. Think of them as ripples in the fabric of space and time itself. These waves spread out across the universe at the speed of light. In 2015, scientists first detected gravitational waves using a system called LIGO. And since then, we've detected several of these events, some from black holes colliding with each other, others from neutron stars crashing into each other. But black hole, neutron star mergers? Those are rarer. And when they do happen, they tell us things we never knew before. The signal they send is different. The pattern of the gravitational waves, the way the wave rises, peaks, and drops, can tell us the size of the black hole, the mass of the neutron star, how fast they were spinning, and how far away the collision happened. These signals are like fingerprints from the collision. They let us peek behind the curtain of reality. Now you're probably wondering, okay, this sounds cool, but why does it matter? Because these collisions might be creating some of the rarest and most important materials in the universe. Some scientists think that when a neutron star gets torn apart, it throws out elements like gold, platinum, and uranium. Stuff we use in electronics. That's right. The gold in your jewelry might have come from a cosmic collision like this. So these mergers don't just shape galaxies. They shape everything, right down to the elements inside your body. And it gets even crazier. Some theories suggest that when a black hole eats a neutron star, it might trigger a short gamma ray burst. This is one of the most powerful forms of energy we've ever recorded. A burst of high-energy radiation that lasts just a couple seconds but can outshine entire galaxies. Gamma ray bursts are terrifying. If one ever went off close enough to Earth, it could literally fry the atmosphere. And we don't even know when or where they're going to show up. That's why scientists are trying to track every merger they can. And it's not easy. Rogue black holes don't leave trails. Neutron stars are hard to spot unless they're spinning fast and beaming radio waves toward us like a lighthouse. These objects are needles in a cosmic haystack. And when they meet, it's over in seconds. Still, we're getting better at spotting them. New observatories like LIGO, Virgo, and CAGRA are working together to triangulate these events. When a wave passes through Earth, these detectors wiggle just a little bit, less than the width of a proton, but enough to tell us something massive just happened light years away. And in 2021, we actually detected 2 black hole, neutron star collisions. That was a game changer. One of them happened about 900 million light years away. Think about that. By the time the wave reached us, dinosaurs had already gone extinct and humans had taken over the planet. This raises even more questions. How often do these collisions happen? Are there more rogue black holes out there than we thought? What about the ones moving toward us? We don't know. We have no idea how many rogue black holes are out there. Some estimates say there could be hundreds of millions in our galaxy alone. Just drifting. Waiting. One could be heading our way right now, and we wouldn't know until it was practically on top of us. Because black holes don't emit light. They just warp everything around them. And if one did get close to our solar system? Let's just say, it wouldn't be pretty. Invisible. Not just dark, not just hard to see, completely undetectable unless they interact with something. That's what makes them one of the most terrifying things out there. They don't emit light, they don't glow, they don't reflect anything. They just drift silently, pulling space itself inward as they go. And they could be anywhere. Literally anywhere. One could be moving through our galaxy right now. One could be heading toward us. And we wouldn't know, not until it started affecting the orbits of stars, or swallowing something in its path. Scientists think there could be millions of these things, quietly roaming the Milky Way. Now combine that with a neutron star. Neutron stars are what's left behind when a massive star explodes in a supernova. The outer layers blow off, but the core gets crushed under its own gravity. We're talking about an object with the mass of our Sun, packed into something the size of a city. To say they're dense is an understatement. Just 1 teaspoon of a neutron star would weigh about 1 billion tons. Let that sink in. These stars don't shine like our Sun. They don't give off warmth in a way that you or I could ever feel. What they do give off are things like X-rays, gamma rays, and in some cases, pulsating radio waves. Some neutron stars spin hundreds of times per second. They're so precise, they're used as cosmic clocks. But when one of these dense monsters crosses paths with a rogue black hole, that's when things get wild. See, most black holes we know about are part of binary systems. They orbit a star, or another black hole, and we detect them by how they affect their surroundings. But a rogue black hole? It doesn't have a partner. It doesn't have something nearby it's visibly eating. It just cruises through space on its own terms. Which is why, when it meets a neutron star, it creates a type of cosmic event that's extremely hard to spot, but massively important. When a rogue black hole merges with a neutron star, we get gravitational waves, ripples in spacetime that were predicted by Einstein over 100 years ago, but only detected for the first time in 2015. These waves stretch and squeeze space itself. They're not sound. They're not light. They're distortions of reality. And when LIGO or Virgo, those giant gravitational wave detectors, pick up these tiny ripples, scientists know something big just happened. But here's the mystery. When two black holes collide, the signal is clean. When two neutron stars collide, we get gravitational waves and light. But when a black hole merges with a neutron star, it's not always so simple. Sometimes we just get the wave. No light. No visible explosion. And that leads to questions. Did the black hole swallow the star whole before it could emit any energy? Or did something else happen? Something we don't understand yet? There's also this. Scientists aren't even sure how often these collisions happen. For a long time, they thought they were rare. Now, with better instruments, they're realizing it could be way more common than we imagined. The first confirmed detection of a black hole neutron star merger came in 2021. And it wasn't just one. It was two separate events, detected just 10 days apart. In one of those, the neutron star was likely swallowed whole. No light. Just a gravitational wave. In the other, there might have been some kind of light signal, but it was too faint to be certain. This opens up a massive information gap. How many of these collisions are happening out there, completely hidden from us? Are we missing out on some of the biggest explosions in the universe because we're only watching with our eyes and not listening with gravitational detectors? Now, imagine what happens during that moment of collision. The black hole's immense gravity starts pulling on the neutron star. If the star gets too close, tidal forces, basically gravity stretching it, can rip it apart. This is called tidal disruption. When that happens, the material of the neutron star can form an accretion disk around the black hole, heating up and giving off light. But sometimes, if the black hole is too massive, it doesn't even give the neutron star a chance to fight back. It just swallows it in one gulp. That's why detecting light from these events depends on a few factors: the size of the black hole, the spin of the black hole, and how fast the neutron star is moving. It's like cosmic chess. Every move depends on the mass, the angle, the speed. And we're only just starting to understand the rules. But here's where the mystery gets deeper. Some scientists believe these collisions could be the birthplace of gold, platinum, and other heavy elements. Think about that for a second. The ring on your finger, the metal in your phone, some of it might have come from a black hole tearing a neutron star apart billions of years ago. That's not poetic. That's physics. When a neutron star gets disrupted, it can throw out huge amounts of neutrons, which quickly fuse into heavy elements. These get blasted into space, and over time, they end up in planets, in people, in everything. But only some black hole neutron star collisions can do this. If the black hole eats the star whole, there's no debris left to spread those elements. So understanding these events isn't just about cosmic fireworks. It's about tracing the origin of matter itself. Now, let's go even weirder. Some theories suggest that under the crushing pressure inside a neutron star, matter gets turned into something even more exotic: quark matter. That's right. If the core is dense enough, neutrons might break down into their components, quarks. If a black hole merges with a neutron star full of quark matter, we might be dealing with physics we've never tested before. It could release forms of energy we don't have the tools to detect yet. Or it might create entirely new types of compact objects that don't even have names yet. And what if, just what if, rogue black holes are searching for neutron stars, not by intention but by gravitational chance? Over billions of years, space gets messy. Galaxies collide. Stars are flung around. The chances of these kinds of encounters go up. And the more of these events we detect, the better we get at answering some of the biggest questions out there. Questions like, what's really inside a neutron star? Are black holes all the same, or do some of them carry hidden properties? Can these collisions tell us something new about dark matter? Can they help us understand how the universe expands? And maybe the biggest one of all, what happens at the exact moment of contact? When the edge of a black hole touches the edge of a neutron star? Do we see physics as we know it break down? Because here's the wild part. Right at that moment, right as the two objects meet, space-time gets twisted in ways we can barely imagine. Gravity is so intense, it's not just pulling matter, it's bending the rules of the universe. If we could watch that moment in real time, what would we even see? Would light stretch into nothingness? Would time slow down? Would we be able to tell where the star ends and the black hole begins? We don't know. And that's why this is one of the biggest space mysteries out there. Actual distortions of the fabric of reality. And when they pass through Earth, they slightly stretch and compress everything, including you, your house, the planet, by microscopic amounts. We've built machines sensitive enough to detect those changes. That's how we know these collisions are happening. But here's the catch. We usually only detect gravitational waves from black holes merging with other black holes, or neutron stars merging with neutron stars. A rogue black hole crashing into a neutron star? That's way harder to spot. Why? Because there's often no light show, no gamma ray burst, no electromagnetic signature. If the black hole is small enough, it might just swallow the neutron star whole, silently, without creating much of a spectacle. All you'd get is a small gravitational ripple. One tiny bump in the cosmic ocean. And if you blinked, you'd miss it. But sometimes, it doesn't go quietly. Sometimes, the neutron star puts up a fight. Let's say the black hole isn't too massive. In that case, when it gets close, the neutron star might start getting torn apart by the black hole's gravity before it's fully consumed. And when that happens, it can release a jet of high-energy particles. Boom, gamma ray burst. And if we're lucky, really lucky, those jets point in our direction and we detect them. But even then, we don't always know exactly what caused it. Was it two neutron stars? Was it a neutron star and a black hole? Or was it a rogue black hole swallowing one? This is where things get tricky. Because most of our instruments are tuned to detect known patterns. We know what a neutron star merger looks like. We know what black hole mergers sound like in gravitational waves. But these mixed mergers? The rogue black hole events? They're still mysterious. Still rare. Still not fully understood. And it gets even more interesting when you realize that rogue black holes don't behave the same way as black holes and binaries. In a binary system, the black hole spirals toward its partner, and we can predict the dance. With a rogue, there's no pattern. It could come in at any angle, any speed. Sometimes it might just fly past. Sometimes it might crash head-on. Sometimes it could even sling the neutron star away with just a gravitational nudge. Now imagine a whole galaxy full of these random black holes. Millions of them. And scattered among them are neutron stars, frozen remnants of dead giants, spinning endlessly in the dark. Every once in a while, purely by chance, one crosses paths with another. And when that happens, the universe shakes. Scientists have long wondered how often this happens. The truth is, we don't know yet. We've only recently developed the tools to start listening. LIGO, Virgo, Cagra, these are the big detectors, listening for gravitational waves. And in 2020, they caught something strange. A signal called GW200105. A gravitational wave from a merger between a black hole and what appeared to be a neutron star. And then, just 10 days later, another one, GW200115. Two possible neutron star, black hole mergers in just 10 days. That was unheard of. Even weirder? One of those events didn't show any light. No explosion. Just a ripple. Which means it could have been a rogue black hole swallowing a neutron star completely. No leftovers, no flare, nothing. Like a cosmic magician swallowing a sword without blinking. And that opens up all kinds of questions. How many of these silent events are happening right now? How many are slipping past our instruments because they're not loud enough? What's going on in the parts of space we can't see? Some scientists think there are entire classes of black holes we haven't even discovered yet. Tiny ones, massive ones, ancient ones. And maybe some of them don't behave the way we expect. Maybe some of them were born in the early universe, before galaxies even formed. Primordial black holes. And maybe, just maybe, some of those ancient rogues are still out there, waiting to crash into something else. And speaking of crashing, what actually happens during one of these mergers? The physics here gets insane. Neutron stars are made almost entirely of neutrons, particles that are normally inside atoms, tightly packed into the nuclei. But in a neutron star, those particles are packed so tightly, it's like a single, giant atomic nucleus. When a black hole starts pulling it apart, that neutron-rich matter gets stretched into long strands called spaghettification. It's not a joke, that's the real word astrophysicists use. Tidal forces stretch the star into thin streams, which spiral into the black hole. And in that process, something incredible might happen. Some of the matter might escape. Not everything falls in. A small amount might get blasted outward. And in that explosion, we might see the birth of heavy elements. Gold, platinum, uranium. The stuff you find on Earth, but made in a collision between two of the most extreme objects in existence. Think about that. The gold in your jewelry? The platinum in electronics? Might have come from a neutron star, black hole collision billions of years ago. That kind of origin story is hard to beat. But there's more. Some physicists believe these collisions could tell us what neutron stars are really made of. See, we still don't know what happens to matter at ultra-high densities. The physics breaks down. Do the neutrons stay intact? Do they break into quarks? Do we get something else entirely, strange matter? Quark soup? These are real questions. And the way a neutron star falls into a black hole might give us answers. By analyzing the gravitational wave signal, how long it lasts, how sharp it is, whether there's a tidal disruption, scientists can infer the internal structure of the neutron star. It's like doing an autopsy on an object we can't see. Every ripple tells a story. But we're just getting started. There's another angle to all this. Rogue black holes don't just merge with neutron stars. Sometimes they mess with entire solar systems. If one passed through our neighborhood, it could throw planets out of orbit. It could strip stars from the galaxy. It could trigger other stars to collide or collapse. We're talking about a cosmic wrecking ball that doesn't even leave a trace of itself behind. Some theories even suggest rogue black holes might help explain dark matter. Not all of it, but maybe part. Dark matter is the stuff we know is there. We can see its gravitational effects, but we don't know what it is. What if a small fraction of it is just rogue black holes we haven't detected yet? And that brings us full circle. Because the more of these rogue collisions we detect, the more we learn about gravity, dark matter, the early universe, and even time itself. Gravitational waves don't just tell us about the objects involved, they tell us about the nature of space. They could help us test whether Einstein's theory of general relativity holds up under extreme conditions. And if it doesn't? That's the start of a whole new kind of physics. But until then, we keep listening. We keep watching. Because out there in the dark, somewhere beyond what our eyes can see, something is falling into something else. And the universe is whispering about it through ripples in the very fabric of reality. And that is just the beginning. Full of stars, black holes, neutron stars, and dark matter, all moving, colliding, interacting in ways we barely understand. Somewhere in that chaos, a rogue black hole starts drifting closer to a neutron star. There's no warning. No glowing light. No heat signature. Nothing. Just a slow gravitational pull that eventually becomes unstoppable. What happens next is one of the most extreme interactions in the universe. As the rogue black hole gets close enough, its gravity begins to stretch the neutron star. This isn't like a balloon popping, it's more like tearing a mountain in half with invisible hands. The atoms in the neutron star start to break down. You've got nuclear material being shredded and flung into space. And because neutron stars are made almost entirely of neutrons, matter so dense it defies imagination, this disruption releases more energy than anything we could ever recreate on Earth. If the black hole is massive enough, it just eats the neutron star in one bite. But if the black hole is smaller, something insane might happen. It might tear chunks off the neutron star first, creating a massive accretion disk of superheated matter spinning around the black hole. This disk shines brightly, mostly in X-rays and gamma rays, and could even produce one of the brightest explosions in the universe. Scientists believe that these types of collisions could be responsible for certain fast gamma ray bursts, the ones that come and go in under 2 seconds. They're rare. They're mysterious. And every time we detect one, we wonder, was that a rogue black hole swallowing a neutron star? Now let's step back for a second. Think about this. These collisions don't just destroy things, they create things. When a neutron star is ripped apart, it releases heavy elements like gold, platinum, and uranium. That's right. The gold in your jewelry, the uranium in nuclear reactors, it might have been forged in the fire of one of these cosmic collisions. Not in a star. Not in a planet. But in the chaos of a black hole merging with a neutron star. So every time one of these events happens, it's not just a violent end. It's a cosmic rebirth. Matter gets recycled. Energy is redistributed. New black holes are formed. And the universe continues to evolve in ways we can barely track. And what about the gravitational waves? Those ripples that pass through the Earth when one of these events goes down? Scientists use massive instruments like LIGO and Virgo to detect them. When they pick up a signal, they can tell where in the sky it came from. But sometimes, the data doesn't match known patterns. The signal's too weird, too short, or too faint. That's when scientists start to suspect this might be a rogue black hole. But here's where it gets even more fascinating. Some researchers believe that rogue black holes and neutron stars might not be rare at all. They might be happening all the time, we just don't see them. Why? Because most of space is dark. Unless the explosion points right at us, or creates detectable waves, we don't even know it happened. The universe might be full of these silent, catastrophic events that are reshaping galaxies right under our noses. And this brings up a bigger question. If these things are happening all the time, what does that say about the stability of our galaxy? Could a rogue black hole eventually pass through our solar system? It sounds like science fiction, but it's not out of the question. Rogue black holes don't follow the rules. They move wherever gravity sends them. If one were to enter the outer reaches of our solar system, we wouldn't notice it until it started pulling on things. Maybe we'd see strange orbits. Maybe we'd notice something was off with comets, or the paths of distant planets. But by then, it might be too late. Still, don't panic. It's incredibly unlikely. But not impossible. The universe is big. Full of danger, mystery, and beauty. And events like rogue black holes merging with neutron stars are just the tip of the iceberg. Cosmic collisions takes place? They don't just tell us that something happened. They tell us how it happened. The frequency, the intensity, the duration of the wave, each one is like a fingerprint. It helps us piece together the exact nature of the event. Was it 2 neutron stars? Was it a black hole and a neutron star? How massive were they? How fast were they moving? How much energy was released? And when we look closely, some of these wave signatures don't match anything we've seen before. They're too fast, or too short, or too faint. That's when scientists start to suspect that we might have just witnessed a rogue black hole, one that came from the dark, crashed into a neutron star, and then disappeared into silence again. But this opens up an even bigger question. Where did the rogue black hole come from? It might have formed in a star system and then been kicked out. When some stars explode, they don't go quietly. The explosion can give the leftover black hole such a powerful kick that it gets launched out of its galaxy, sent drifting forever through interstellar space. That's one way to make a rogue. Another possibility is even weirder: primordial black holes. These are black holes that might have formed in the very early universe, just fractions of a second after the Big Bang. They wouldn't have come from stars. They would have come from raw fluctuations in density, tiny blips in the early universe that got so dense they collapsed in on themselves. If primordial black holes exist, they could be anywhere. And they might be some of the rogue black holes crashing into neutron stars right now. And the neutron stars? They could have had lives of their own before the collision. Some of them might have been pulsars, spinning rapidly and sending beams of radio waves across the galaxy like lighthouses. Others might have been magnetars, neutron stars with magnetic fields so strong they can tear apart atoms. When a rogue black hole merges with one of these exotic stars, we're talking about a showdown between two of the most extreme objects in existence. And we're only scratching the surface. Because these events don't happen in isolation. The gravitational shockwaves they send out can affect nearby stars. The energy they release can heat up interstellar gas. Some scientists even speculate that they might trigger star formation by compressing nearby clouds of hydrogen. So a rogue black hole merging with a neutron star doesn't just change the two objects involved. It can change entire regions of space. It can reshape galaxies, ripple through time, and compressing surrounding gas clouds with their shockwaves. Think about that for a second. A black hole, wandering alone through space, eventually collides with a neutron star, unleashes unimaginable energy, and that energy goes on to spark the birth of new stars. Death causing life. Cataclysm triggering creation. It's a cycle written across the universe, one that repeats in silence and darkness, far beyond what we can see with our eyes. But the thing is, we don't actually see most of these events. That's the haunting part. The universe is massive beyond comprehension, and our instruments only detect a fraction of what's out there. We are, quite literally, listening through a crack in the wall, trying to understand the symphony being played on the other side. Rogue black holes aren't part of well-behaved star systems where we can track their movement. They don't orbit predictably. They don't emit light. They don't follow rules. They just float, waiting to be pulled into something bigger or slam into something smaller. If we do detect them, it's usually only because of what they destroy, not what they are. And even then, most of the time, we miss them. The gravitational waves might be too weak, the light too faint, the explosion too fast. This is why we've started building better and more sensitive detectors. The current generation of observatories like LIGO and Virgo have already changed how we understand black hole and neutron star mergers. But the next generation, like the Einstein telescope in Europe or the Cosmic Explorer in the US, could detect these mergers from across the entire universe. They might pick up not just the obvious ones, but the weird ones, the quiet ones, the rogue ones. Imagine a day when we can listen to the universe like we listen to music. Not just the loud crashes, but the soft whispers in between. And there's another layer of mystery here, something that's becoming more and more relevant. Some scientists believe that rogue black holes merging with neutron stars might also help us answer one of the biggest questions in physics: what happens inside a neutron star? We know they're made of incredibly dense matter. But we don't actually know what kind of matter exists in the center. It might be just neutrons packed tightly together. Or it might be something stranger: quark-gluon plasma, exotic particles, or even states of matter that don't exist anywhere else in the universe. When a black hole merges with a neutron star, that core is torn apart and swallowed. If we can study the gravitational wave closely enough, we might be able to figure out what that core was made of. That's like doing surgery on an object that's thousands of light years away, using only ripples in space as your tools. It's insane. And yet, we're getting close to being able to do it. But the deeper we dig, the weirder it gets. Because as we start to understand these collisions, we start to realize they might not be rare at all. What if they're happening all the time? What if rogue black holes are more common than we thought? Think about how many stars there are in the Milky Way, over 100 billion. A certain percentage of those will go supernova and become neutron stars. Another portion will collapse into black holes. Some of those black holes will be ejected from their systems. Statistically speaking, collisions should happen. Not just once in a blue moon, but often. And not just in distant galaxies either. Maybe in ours. Maybe nearby. Maybe there's a rogue black hole drifting toward our region of the galaxy right now, silent and invisible, on a path that will one day intersect with a neutron star and create a flash so bright it outshines everything else in the sky. And we won't know until it happens. This possibility isn't just theoretical. In fact, astronomers have already identified several black hole candidates that appear to be isolated, no companion star, no surrounding matter. They're only detectable because of their gravitational influence on nearby stars. These are the kinds of objects that could eventually crash into neutron stars. But we need better tools to track them, better simulations to predict their behavior, more powerful computers to analyze their gravitational signatures. That's why this field is so exciting right now. Every new upgrade to our detection systems brings us closer to understanding one of the strangest, most violent phenomena in the universe. But there's something even more mind-bending. Some physicists speculate that rogue black holes merging with neutron stars might produce not just gravitational waves and gamma-ray bursts, but something even stranger, echoes in space-time. After the initial collision, after the wave has passed, there might be faint reverberations, tiny ripples that bounce around the black hole's event horizon before fading away. If we can detect those echoes, we might be able to test ideas about quantum gravity and even Hawking radiation. That would mean merging black holes and neutron stars could become experimental labs for the biggest questions in science. What is space-time? What is the nature of gravity? Is the event horizon really the end of the universe as we know it? And now, we reach a point where science starts to blur into philosophy. Because when you talk about rogue black holes, these wandering, invisible entities crashing into objects made of the densest matter in the universe, you start to question everything. What is mass? What is time? What is energy? What is reality when something that weighs millions of times more than the Earth can float silently across the galaxy, colliding with a neutron star and creating a ripple that passes through your body right now without you even noticing? That's the universe we live in. It's not quiet. It's not still. It's not safe. It's violent, unpredictable, and full of things we still don't understand. And maybe that's the most exciting part of all. Or even entirely new states of matter that we've never observed before. When a neutron star is disrupted by a black hole, those inner layers, the very core of the star, can be torn apart and flung into space. For a fleeting moment, the universe puts those secret materials on display. If we can capture the radiation, the gravitational waves, or even neutrinos released in that exact moment, we might finally peek into the fundamental structure of matter at its most extreme. That's not just cool science, that's revolutionary. It could redefine how we think about particle physics, nuclear forces, and maybe even gravity itself. And speaking of gravity, there's something else. These events might be the best testing ground we have for Einstein's theory of general relativity. In most cases, general relativity works like a charm. It explains how gravity bends light, how planets orbit stars, how black holes warp spacetime. But we've never had a great way to test it in the strongest gravitational fields possible, until now. A rogue black hole slamming into a neutron star is one of the most extreme gravitational interactions that can occur. If there's even the tiniest flaw in Einstein's theory, it might show up in the aftermath of one of these collisions. Maybe the gravitational waves arrive just a bit too early or late. Maybe the energy radiated doesn't match the predictions. Maybe the merger forms a black hole that spins faster than physics allows. All of these things would be clues, hints that the universe might be running on deeper laws we haven't uncovered yet. Now let's talk about detection for a moment, because it's easy to forget how hard it is to actually catch one of these events in real time. A rogue black hole is invisible by itself. A neutron star is small and faint unless it's a pulsar. And space is huge. So scientists use networks of observatories around the world, and in space, to scan the sky for changes. Telescopes look for sudden gamma-ray flashes, X-ray emissions, or bursts of light in optical wavelengths. Meanwhile, gravitational wave detectors are constantly listening for ripples. When something suspicious is picked up, an alert goes out to the global scientific community, and a coordinated effort begins to point every possible telescope at that region of the sky to see what's happening. Sometimes, they get lucky. In 2019, scientists detected a gravitational wave signal called GW190814 that sparked a frenzy. It seemed to come from a merger between a black hole and a mysterious object about 2.6 times the mass of the Sun, too heavy to be a neutron star, too light to be a typical black hole. No light was detected, just the ripple in space-time. Was that object a neutron star? A primordial black hole? A completely new class of star? We still don't know. But that's the beauty of these events. They raise questions no one's even thought to ask. And beyond the questions of physics, there's the sheer awe of what's happening. These collisions are rare. They might only happen a few times a year in a galaxy like ours. But the universe has billions of galaxies. That means somewhere, right now, a black hole might be drifting through interstellar space, slowly approaching a neutron star that's been silently spinning for millions of years. They don't know they're on a collision course. There's no warning. No sound. No light. Just two monsters getting pulled together by a force they can't escape. And when they meet, the entire region of space will change forever. That's the part that hits hardest. These aren't just events on paper. They're not simulations or ideas. They're real. They're happening. And the consequences echo through the universe in ways we're just beginning to understand. That didn't quite fit the usual profile. It wasn't a clear black hole merger, and it wasn't a standard neutron star collision either. The signal was odd, shorter than expected, but too heavy to be just neutron stars. After analyzing the data for months, scientists came to a fascinating conclusion. It might have been the first recorded instance of a black hole swallowing a neutron star. No warning, no light show, just a sudden, clean signal, a ripple in space-time, and then silence. The neutron star may have been consumed whole, without being torn apart first. If true, this would have marked one of the cleanest, most mysterious examples of cosmic cannibalism. And it left behind barely a trace. Now imagine how many of these events are happening all around us, completely undetected. Our current instruments are limited by distance, direction, and sensitivity. But as technology improves, we might begin picking up thousands of such collisions every year. And the more data we collect, the more we start to see patterns. How often these mergers happen, where they happen, what kinds of galaxies they occur in. Maybe we'll learn that rogue black holes prefer certain environments, regions with low star density, where gravitational slingshots could be common. Maybe we'll find that neutron stars are more fragile than we thought, often consumed without a trace. Or maybe we'll find something completely unexpected, a third object, strange timing, repeating events. It's not just about black holes and neutron stars anymore. It's about understanding how the whole cosmos evolves through violent transformation. When these collisions happen, they release more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. That kind of power isn't just a spectacle. It moves matter across galaxies. It stirs magnetic fields. It seeds space with heavy elements like gold, platinum, and uranium, materials that literally end up in our hands, our electronics, even our bones. In other words, we are made, in part, from the aftermath of rogue black holes crashing into neutron stars. We wear their violence. We carry their history. But even with all this knowledge, the truth is, we still don't know what happens right after the merger. What's left behind? A bigger black hole? A strange new kind of star? Or something we don't have a name for yet? Theoretical physicists are starting to speculate about transitional objects, temporary monsters born in the chaos, lasting only milliseconds before collapsing under their own weight. Some of these might mimic the properties of both black holes and neutron stars. Others might be completely outside current physics, objects so dense, their matter exists in unknown states, beyond anything seen in labs. And here's where things get even wilder. If some theories are correct, certain mergers between rogue black holes and neutron stars might briefly create conditions similar to the Big Bang: extreme temperature, pressure, and density. In that moment, space itself might behave differently. Particles might appear and vanish. Time might stretch. The rules of physics, as we know them, might not apply at all. These moments might be the closest we can ever get to observing the birth of the universe without a time machine. And through them, we might uncover answers to the deepest questions we've ever asked. Where did we come from? Why is there something instead of nothing? Is the universe repeating itself? About all sorts of exotic outcomes. Some believe that under the right conditions, the collision might not instantly form a black hole. Instead, it could create something called a hypermassive neutron star, a temporary object that defies gravity for a few moments before collapsing. This object would be spinning at insane speeds, generating the most extreme magnetic fields in the universe. For a brief moment, it could become a magnetar on steroids, radiating powerful gamma-ray bursts and sending shockwaves through surrounding space. These transient monsters could be the missing link in explaining mysterious high-energy events we still can't identify. Short gamma-ray bursts, fast radio bursts, or even some of the odd cosmic ray anomalies we've detected. And then there are the theorists who take it even further. What if the collapse of a neutron star into a black hole doesn't just end in darkness? What if, at that moment of ultimate density, something else happens, something beyond the standard laws of physics? Some have speculated that the merger could rip open a tear in the fabric of spacetime itself. Not just a black hole, but a wormhole, a gateway to somewhere else. It sounds like science fiction, but there are equations that allow for this possibility under extreme conditions. The energy, density, and curvature of spacetime involved in these mergers are unlike anything else we know of. If there's any place in the cosmos where the impossible could happen, it would be there. Others have suggested that such a collision might create a naked singularity. Normally, a black hole's singularity, the point where gravity becomes infinite, is hidden behind an event horizon. But under very specific scenarios, like an off-axis collision or an uneven mass ratio, the event horizon might fail to form properly. This would expose the singularity directly to the universe, a concept that challenges the very foundation of general relativity. If that ever happened, we'd be seeing physics raw, unfiltered, and completely untamed. It would be like lifting the veil on the most forbidden part of the universe. And if we ever detected one, it could either prove Einstein right, or tear his entire theory apart. And while all of that sounds distant and hypothetical, there's a deeply personal angle to it too. Because the elements scattered by these mergers don't just float through space. Eventually they cool, clump together, and become part of the next generation of stars and planets. Some of that material ends up on planets like Earth. Some ends up inside living beings. That means it's entirely possible that part of you, your blood, your bones, your brain, once belonged to a star that was shredded by a rogue black hole billions of years ago. You, sitting here now, listening to this, might carry inside you the ashes of a dead neutron star. You might be, in a very real way, the memory of a cosmic collision. Let that sink in. The mystery of space isn't just about what's out there. It's about what's already inside us. We're made from this chaos. We're the calm that comes afterward. And that idea, this fusion of destruction and creation, might be the most hauntingly beautiful part of it all. Because every time we look up at the stars, we're looking at the past. At things that died so that new things could live. And somewhere out there, right now, in the deep silence between galaxies, another rogue black hole is drifting, aimless, waiting for the next neutron star to cross its path. Planets. That means the gold in your ring, the platinum in your electronics, and even the iodine in your thyroid could all trace their origins back to one of these violent events. We don't usually think about it, but the materials we interact with every day, luxuries, tools, even things critical to life itself, might have been forged in a moment where a rogue black hole slammed into a neutron star at a fraction of light speed, crumpling matter, tearing spacetime, and exploding across the cosmos with a force no human can truly comprehend. That alone should make you stop and think. Every time you touch a metal object, you're literally holding a piece of stellar violence, condensed into something silent, solid, and useful. It's humbling, isn't it? That our entire world is built on the backs of dead stars and collapsed gravity. But it also speaks to how small we are, and how little we still know. Because for all our models and guesses, we've never actually seen one of these events in clear, visible light. That's the problem. When a black hole collides with a neutron star, the outcome is heavily influenced by mass ratio and spin alignment. If the black hole is too massive, it simply swallows the neutron star whole before the star can even emit any light. That's a dark merger, almost invisible, except for the gravitational wave signal. But if the black hole is a bit smaller, and especially if it's spinning rapidly in the right orientation, it can tear the neutron star apart before fully consuming it. In those rare cases, we might actually get a flash of visible light. But catching it? That's the real challenge. Because we have to detect the gravitational wave signal first, and then scramble dozens of telescopes around the world to look at that tiny patch of sky. And we usually only have minutes, sometimes seconds, to do it. Add to that the fact that the sky is massive, and these events are rare, and it becomes a cosmic needle in a haystack problem. But once we do catch it, once we actually see one happen in visible light, infrared, X-ray, and gamma ray all at once, it'll be a game changer. That single multi-messenger detection could teach us more than a decade of theory ever could. It's the equivalent of not just hearing thunder, but seeing the lightning, feeling the wind, and watching the entire storm unfold all at once. So far, we've had hints. One possible detection in 2020 suggested that a neutron star might have been torn apart just before it was swallowed. The light was faint, and we didn't catch it immediately, but it was enough to get the astronomy community buzzing. If true, it confirmed that under the right circumstances, black hole, neutron star mergers could leave visible fingerprints in the universe. It also told us that rogue black holes, those not anchored to galaxies or big structures, might be more common than we thought. After all, if they were rare, we wouldn't be seeing even hints of these events so early in our detection history. That's the exciting part, we're just getting started. The more sensitive our detectors become, the more of these collisions we'll uncover. And each one will add a new piece to the cosmic puzzle. Let's talk more about what makes a rogue black hole truly rogue. These are objects with no home, no orbit, no allegiance to any solar system or galaxy. They've been flung out, ejected by powerful gravitational encounters, or left wandering after their host galaxy was disrupted or merged with another. Some are kicked out by the very events we've been talking about. When two massive stars go supernova in a binary system, the resulting neutron star or black hole can receive a kick, a powerful momentum that shoots it off into space. Sometimes the velocity is enough to escape the gravitational pull of their galaxy. That's how you get a rogue black hole, a dark, silent object moving through intergalactic space, invisible until it interacts with something else. And what's terrifying is how common they might be. Some simulations suggest that our own galaxy could contain over 100 million black holes. Most of them are stellar mass, formed from dying stars. And while many of them might be locked into stable orbits around the galactic center, a significant portion are drifting. Unseen, unfelt, untethered. If even a small fraction of those are on rogue paths, that means there could be thousands of these things just wandering the Milky Way, moving silently through the void, occasionally passing near stars, clouds of gas, or, rarely, other compact objects like neutron stars. And when those rare meetings happen, we get the kind of cosmic fireworks that change everything. The rogue black hole, traveling at thousands of kilometers per second, might begin to gravitationally interact with a neutron star that was itself just drifting in the outskirts of a stellar nursery, or a dying cluster. The two objects, initially strangers, begin a dance, spiraling closer and closer over hundreds of thousands of years. They warp space-time around them, leaking energy through gravitational waves, tightening their orbit until, finally, one consumes the other in a burst of energy that can outshine an entire galaxy for a brief moment. But here's the real kicker. We don't know what's happening inside that final moment. Neutron stars are made of matter so dense, a teaspoon would weigh 1 billion tons. That's nuclear-level density. And some theories suggest that at their core might be something even stranger, quark matter, or even a form of matter we haven't identified yet. When a black hole collides with a neutron star, that strange core matter might be exposed, or it might alter the collapse process in unpredictable ways. It might change the shape of the black hole itself, cause it to ring in unusual gravitational wave frequencies, or even emit a burst of exotic particles we've never seen before. We're entering the frontier here, where known physics ends and speculative science begins. And if those ideas aren't wild enough, some fringe physicists have proposed that black hole, neutron star collisions might offer clues about dark matter itself. What if, buried deep inside these collisions, we're seeing interactions that hint at particles beyond the standard model? What if some of the mass energy we detect, missing, in these collisions is actually going into creating or disturbing dark matter particles? We wouldn't be able to see it directly, but the math might not add up, and that's the point. When the math doesn't balance, nature is trying to tell us something. Some anomalies in gravitational wave data might already be whispering about these possibilities. And this leads us to a deeper, more unsettling question. What if rogue black holes aren't just drifting through space? They're shaping it. Over billions of years, these wanderers might be subtly influencing the structure of galaxies, the formation of stars, and the evolution of planetary systems. Their gravitational influence, though invisible, could shepherd gas clouds, trigger supernovae, or disrupt entire solar systems. They could be playing a silent, yet powerful role in the story of the universe, a role we've only just begun to recognize. And the more we look, the more we might discover that these rogue objects aren't just accidents. They might be essential parts of how the universe evolves and regenerates. And smelling the ozone all at once, it gives us the full picture. And once we get that, we'll finally be able to say not just that these mergers happen, but exactly how they happen, what they create, and how often they've shaped the universe we live in. Scientists are itching for that moment. They're tuning their instruments, upgrading their observatories, and even planning missions to orbit with telescopes that will constantly watch the sky in ways we couldn't before. Because the first time we get a full spectrum view of a rogue black hole merging with a neutron star, it won't just be data, it'll be history. But let's take a step back for a second and really think about the black hole in all of this. Not the usual kind that sits at the center of galaxies or forms from dying stars and binary systems, but the rogue ones. The loners. These are the black holes that aren't tied to any star, any orbit, or any structure. They're just out there, drifting in the void. Scientists estimate there could be millions of these rogue black holes in our own galaxy alone. They're completely invisible unless they interact with something. No light. No heat. Just gravity. Silent predators moving through the dark, and we're only beginning to understand how many of them are out there. How do they go rogue? Well, it's not always by choice, if a black hole can be said to make choices. Sometimes, a black hole is born from a massive star-going supernova in a binary system. When that explosion happens, it can kick the newly formed black hole away at tremendous speeds, thousands of kilometers per second. That's enough to fling it out of its original orbit and send it on a solo journey through the galaxy. Other times, galaxies collide, and the gravitational chaos can sling black holes out into intergalactic space. And sometimes, when two black holes merge, the violent release of energy in gravitational waves can create a recoil effect, like a gun kicking back, and launch the resulting black hole far away from its origin. Whatever the reason, these rogue black holes are dangerous in a way that's completely different from the ones we usually study. Because they're unbound, they can travel through gas clouds, disrupt star formation, even potentially pass through solar systems like our own. If a rogue black hole ever passed close enough to our Sun, it could throw off planetary orbits, or send objects from the Oort cloud raining into the inner solar system. If it passed through the Milky Way's dense stellar disk, it could trigger chaos on a scale we're not ready for. And if one ever got close enough to a neutron star, well, now we're talking about the kind of collision that creates the rarest and most mysterious events in the universe. What makes the merger of a rogue black hole and a neutron star even more special is the unpredictability. With binary systems, we can at least estimate mass ratios, orbital decay, and spin orientation because they're tied to one another and influence each other over time. But when a rogue black hole smashes into a neutron star, all bets are off. There's no elegant dance, no spiraling death spiral. It's a sudden, brutal encounter, pure cosmic violence. The neutron star doesn't see it coming. The black hole might not even be aligned properly. The result? A messy asymmetrical event that defies modeling. Some theorists argue that such collisions could create distorted, lopsided black holes, ones that wobble, ring, and emit gravitational waves unlike any we've ever seen. Others suggest it could result in fragments of the neutron star being ejected at relativistic speeds, almost the speed of light, launching jets of exotic particles across the universe. And here's another mind-blowing twist. Some simulations have shown that in extremely rare cases, when the mass ratio and velocity are just right, the neutron star might not be completely consumed. Instead, a piece of it could survive, flung away, compressed, maybe even made more stable. We could be looking at the creation of a strange star. These hypothetical objects are thought to be made not of neutrons, but of even smaller particles called quarks, up, down, and strange quarks compressed into a state of matter so dense and stable that it could last indefinitely. If such an object formed, it would be the first of its kind ever discovered. And if we could find one, if we could detect its unique fingerprint, it would rewrite our understanding of what matter can be. This is the kind of frontier we're standing on right now. The edge of what we know and what we don't. Every rogue black hole out there is a potential mystery waiting to happen. Every neutron star drifting through space is a ticking time bomb of cosmic potential. And when they collide, when the unpredictable meets the extreme, that's when the universe gives us its deepest secrets. Not through calm observation, but through chaos, destruction, and rebirth. And even more fascinating is the long-term consequence of such collisions. After the dust settles, after the light fades and the gravitational ripples echo into the void, what's left behind doesn't just vanish. The newly formed black hole might go on drifting through space, even heavier now, maybe spinning faster than before. And the surrounding region could be forever changed. Gas clouds disrupted. Star formation halted, or sparked. Elements scattered across light years. Entire solar systems could be thrown off balance. Planets might be ejected, moons torn apart, new stars born from the remnants of old ones. One event, just one, can reshape a whole chunk of the galaxy. And think about this, somewhere out there, right now, this could be happening. A rogue black hole might already be closing in on a neutron star, unseen by any telescope, moving silently through a void so vast it makes everything on Earth feel like a grain of dust. The collision could happen tomorrow. Or maybe it already happened thousands of years ago, and the signal is just now reaching us, traveling through the fabric of space at the speed of light, waiting to be picked up by our detectors. What will it show us when it arrives? What kind of story will it tell? We don't know yet. But we're watching. We're listening. To our solar system, it wouldn't need to collide with anything to cause chaos. Its gravity alone would be enough to start pulling planets off course, distorting orbits, and possibly sending entire worlds hurtling into deep space. The Earth might not be swallowed, but the balance that makes life possible could be destroyed in a slow, invisible catastrophe. And the terrifying part? We might never even see it coming. No light. No warning. Just subtle shifts in planetary motion that only the most precise instruments might detect. By the time we noticed, it could already be too late. This is why scientists take the idea of rogue black holes seriously. Not just because they're dangerous, but because they could be incredibly common, and we don't really know how many there are. Some astronomers are trying to spot them indirectly by looking for signs of gravitational lensing, where the black hole passes in front of a distant star and bends its light, like a magnifying glass. But this method is tricky, rare, and only works in very specific alignments. The truth is, most rogue black holes will never be detected unless they do something dramatic, like merge with a neutron star. Now let's talk about that neutron star for a second. It's easy to gloss over what a neutron star really is, but it's one of the most extreme objects in the entire universe. Imagine taking something more massive than the Sun and crushing it into a sphere just 20 kilometers wide. That's smaller than most cities. The result is an object so dense that a single teaspoon of its material would weigh about 1 billion tons. The gravity is so intense, time itself slows down near its surface. Its magnetic field is trillions of times stronger than Earth's. Some of them spin hundreds of times per second, flashing beams of radiation like cosmic lighthouses. And when something like that meets a rogue black hole, you've got one of the most violent, rare, and mysterious events in the cosmos. This isn't just a collision, it's a physics experiment that no human could ever recreate. The black hole starts to tear the neutron star apart. Depending on the angle, the spin, the mass ratio, this can either happen slowly or all at once. Matter from the neutron star spirals into the black hole in an accretion disk, heating up, emitting bursts of X-rays and gamma rays, and possibly forming short gamma-ray bursts, some of the most energetic explosions in the universe. And the things we learn from these bursts? They can rewrite entire chapters of physics. We study the light signatures to understand what elements are being formed. We measure the gravitational waves to learn about the size and structure of neutron stars. We analyze the debris clouds to look for clues about the equation of state for nuclear matter, basically, how matter behaves when you push it beyond any known limit. These are the kinds of things we can't test in a lab. Only nature can create these conditions, and we just have to catch them in the act. But even beyond the science, there's something awe-inspiring about it. These aren't just events happening out there. They're shaping the very structure of the cosmos. They're creating the elements we need to exist. They're rewriting the rules of what we thought we knew. Every time a rogue black hole collides with a neutron star, the universe becomes a little more mysterious, and a little more beautiful. What's known as a relativistic jet, a beam of matter and energy traveling close to the speed of light. That jet might last for seconds or minutes, and in that brief flash, it could outshine entire galaxies. And here's the wild part. That flash might be the only clue we ever get. If the jet is pointed in our direction, we might detect it as a short gamma-ray burst, which is one of the most energetic events in the universe. But if the jet points somewhere else, we could miss it entirely, and the event would pass us by unnoticed. Now, depending on the mass of the black hole and how fast the neutron star is spinning, there's a chance that the neutron star might not get swallowed immediately. It could be stretched and ripped apart over a longer time, throwing out debris rich in heavy elements. This debris, full of neutrons and atomic nuclei, can lead to something known as a kilonova, an enormous explosion that's about 1,000 times brighter than a typical nova. This is where some of the universe's heaviest elements are forged. Gold, platinum, uranium, elements that we value deeply, may have been born in the fires of these collisions. That means every gold ring, every piece of platinum jewelry, every speck of uranium used for power or science, might have originated from an ancient collision between a rogue black hole and a neutron star billions of years ago. And this brings us to a strange realization. The rarest, most violent events in the universe aren't just distant fireworks. They're part of our story. We carry their remnants in our bones, in our tools, in the earth itself. The birth of the elements that make up our world may trace back to these cosmic smash-ups. That's why astronomers are obsessed with finding more of them. Not just because they're exciting or dramatic, but because they tell us where we come from. But there's still so much we don't know. Like what happens after the merger. If the black hole isn't too massive, and if the neutron star is spinning fast enough, it might briefly resist collapse. For a few milliseconds, or maybe even seconds, it could become a hypermassive neutron star, an object even stranger and more unstable than anything we've ever directly observed. It might wobble, spin, emit gravitational waves, and then suddenly collapse into a black hole, releasing a final burst of energy. The exact sequence depends on so many variables: mass, spin, magnetic field, angle of approach, even the temperature of the star's core. Each of these factors creates a different outcome. That's why no two mergers are exactly alike. One might produce a short gamma-ray burst, another might not. One might form a visible kilonova, another might be completely dark. It's like trying to study lightning by watching it strike in different places, under different conditions, and hoping you catch the pattern. But we're getting better. With more gravitational wave detectors online, like LIGO, Virgo, and CAGRA, and more sensitive telescopes scanning the skies, our chances of catching these events in real time are increasing. Eventually, We might be able to not only detect the merger but also map the exact dynamics of what happens second by second. That kind of detail could unlock new physics, maybe even hints of quantum gravity, or exotic forms of matter that only exist in these extremes. Scientists are already running simulations on supercomputers, trying to model every possible outcome. They're feeding in equations that account for relativity, thermodynamics, quantum mechanics, all of it, just to understand what happens in those few final seconds before the neutron star is completely consumed. And then there's the aftermath. What does the surrounding space look like after the merger? What happens to the magnetic fields, to the leftover material, to any nearby stars or planets? Could a nearby planet be blasted with radiation or even stripped of its atmosphere? Could a merger trigger star formation in a gas cloud light years away? These are the kinds of questions scientists are beginning to ask, not just how these collisions happen, but what ripple effects they send across the galaxy. Even now, we're probably missing dozens of these events every year. They're happening in distant galaxies, or behind clouds of dust, or in directions we're not watching. Each one a cosmic drama unfolding in silence and darkness. That's why the next generation of observatories, space-based gravitational wave detectors like LISA, or massive new radio telescopes like the Square Kilometre Array, will be crucial. They'll give us eyes and ears everywhere, helping us catch more of these fleeting moments and piece together the full picture. Because every time a rogue black hole merges with a neutron star, the universe changes just a little. And with every detection, so do we. A final, cataclysmic burst of energy as its core gives in to the unstoppable pull of gravity. This moment, the collapse of a hypermassive neutron star into a black hole, is one of the most extreme transitions in the universe. We're talking about the very limits of matter and space-time. It's not just that mass is being compressed, reality itself is being twisted. Time dilates. Space curves. Physics, as we know it, starts to break down. It's like peering into a part of the universe where the rulebook gets torn apart. And what's even more fascinating is what we might detect from that final death spiral. While telescopes might catch the light, the real revelation comes from gravitational waves, ripples in the fabric of space-time itself. These waves don't carry light. They carry movement. Disturbances. Echoes of mass being shifted violently and suddenly. The LIGO and Virgo detectors on Earth have already picked up signals from neutron star mergers, and even black hole collisions, but detecting a merger between a rogue black hole and a neutron star? That's the holy grail. Because it would give us a whole new type of signal, a unique waveform that tells the story of mass transfer, tidal disruption, possible jet formation, and collapse, all in one chaotic event. These gravitational waves are like fingerprints. Each one is different. Each one tells us the mass of the objects involved, how fast they were spinning, what angle they collided at. It's a language of the cosmos that we're only just beginning to understand. And if we can detect more of these rare collisions, we might finally answer some of the biggest questions in astrophysics. Like, what happens to matter at the highest possible densities? Is there a limit to how massive a neutron star can be before it becomes a black hole? Do black holes grow faster by feeding on stars, or by merging with other massive objects? And maybe even deeper, what do these mergers say about the evolution of the universe itself? Because if rogue black holes are more common than we thought, and if they've been gobbling up neutron stars for billions of years, then the cosmic landscape might be shaped by these silent, invisible predators far more than we ever imagined. Galaxies might have missing stars because they were swallowed. Pulsars might vanish not because they burned out, but because a wandering black hole drifted too close and ended them in a moment. That's a terrifying and awe-inspiring thought, that some of the universe's brightest beacons could be snuffed out by things we can't even see coming. What's even wilder is that some of these events might have already happened in our own galaxy. Not millions of light years away, but nearby, in galactic terms. A black hole might have devoured a neutron star somewhere in the Milky Way, sending out a burst of gamma rays and gravitational waves that we missed simply because we weren't looking in the right direction or didn't have the right instruments online at the time. It's like the universe is throwing fireworks displays behind our backs, and we're only catching glimpses and reflections. This is why the future of space exploration is going to be as much about listening as it is about looking. New telescopes like the James Webb are giving us deeper visual insight than ever before. But the real breakthroughs are coming from gravitational wave astronomy, from neutrino detectors, from radio observatories that can scan entire regions of space for strange, repeating signals. We're entering a time where we don't just see the universe, we feel it, we hear its pulses, its crashes, its echoes. And somewhere in all that noise are the signatures of rogue black holes slamming into neutron stars. But even if we catch one of these events in real time, even if we record every last signal it emits, we still run into a wall. Because the physics inside a neutron star, or at the event horizon of a black hole, isn't just extreme, it's unknown. We don't fully understand how matter behaves under such pressure. We don't even know if Einstein's equations hold up in those conditions. For all we know, the inside of a neutron star could contain a form of matter we've never seen before, quark-gluon plasma, or strange matter, or something even more alien. Some theories suggest that a neutron star merging with a black hole might not be the end, but a doorway. That's right. There are physicists who believe that if a neutron star collapses under the right conditions, it might trigger something beyond just a black hole. Maybe a wormhole. Maybe a baby universe. Maybe even a white hole, theoretical opposites of black holes that explode matter outward instead of sucking it in. These ideas are fringe, but they're not science fiction. They come from the math. From the models. From the limits of what we know and what we don't. And every time a new merger is detected, every time we get a new gravitational wave signature or light curve, we're testing those theories against reality. So think about this, somewhere out there, drifting silently through the void, is a rogue black hole, undetectable, cold, invisible. It might be the size of a city, with a mass of multiple suns. And somewhere else, spinning like a cosmic beacon, is a neutron star, an ultra-dense corpse of a supernova, blazing with radiation and magnetism. The two are on a collision course, maybe now, maybe tomorrow, maybe a million years from now. When they meet, the universe won't just witness destruction, it'll witness creation. Of heavy elements. Of gravitational waves. Of mystery. And we, down here on our tiny planet, will catch just a whisper of it, if we're lucky. Consume them without a trace. This changes the way we look at star populations and galaxies. It changes how we calculate stellar lifespans. It even changes how we think about the balance of matter in the universe. Because if black holes are silently absorbing neutron stars across galaxies without leaving behind visible clues, then we've been underestimating how much mass has already disappeared into the void. We might be surrounded by way more black holes than we ever thought possible, hidden in plain sight, roaming the cosmos, swallowing the most exotic matter that exists. And here's something even crazier: rogue black holes don't always stay quiet. If they pass through a gas-rich region, say, the dense clouds near the core of a galaxy, they can light up. Not because they glow, but because the material they pull in heats up and radiates energy. That gas spiraling inward forms an accretion disk, which can become hotter than the core of most stars. For a brief time, these dark wanderers can blaze like quasars, spewing X-rays and gamma rays into space. But once they've had their meal, they vanish into silence again. It's like a cosmic game of hide and seek, where the seeker never stops moving and the only sign they were ever there is a flash that fades before you even know what happened. Now imagine the neutron star's point of view. This is an object made entirely of neutrons, crushed into a sphere just a few kilometers across. A single teaspoon of its material would weigh billions of tons. It spins rapidly, sometimes hundreds of times per second. It has a magnetic field trillions of times stronger than Earth's. It's a survivor of a supernova, a remnant of an exploded star. And yet, despite all that power, when a black hole creeps near, the neutron star is helpless. Its immense gravity can't protect it. Its rapid spin can't save it. The black hole begins pulling it apart, bit by bit, until what's left is either sucked in completely, or scattered into space as glowing debris. And it's in that debris, in the wreckage of a shattered neutron star, that the seeds of new elements are born. As the tidal forces rip apart the neutron star, neutrons are freed and slammed into atomic nuclei, creating the heaviest elements in the universe. This is called our process nucleosynthesis. It's a fancy term, but what it really means is that the universe has its own forge. It doesn't just make stars and planets. It makes the stuff of legends, gold, platinum, rare earth metals. And it only happens in the most violent collisions we know. So when you see someone wearing a gold necklace, or holding a platinum ring, you're looking at a piece of a neutron star that died in the arms of a black hole. You're seeing the aftermath of destruction so intense it created beauty. That's what makes these events so incredible. They're not just cataclysmic, they're creative. They take the densest, darkest things in the universe and turn them into the raw materials for new worlds. And here's the thing, this isn't just a one-time event. This could be happening all the time. Somewhere in the universe, right now, a rogue black hole might be stalking its next target. And because black holes don't emit light, we might not know until it's already begun. The neutron star might suddenly vanish from radio telescopes. Or we might see a brief flash of gamma rays. Or we might feel the tremor of space-time, a gravitational wave, rippling across the universe. It's a cosmic crime scene with invisible culprits and fleeting clues. That's why scientists are pushing hard to build better detectors. Bigger telescopes. More sensitive gravitational wave observatories. Because they want to catch these collisions in the act. They want to watch the process unfold in real time, to map the energy released, to study the debris. And more than anything, they want to understand the laws that govern the universe at the extremes. Because these events push everything to the limit: mass, pressure, spin, magnetism, and space-time itself. And if we can understand that, we might understand everything. We might finally get answers to questions that have haunted physics for over a century. What happens at the edge of a black hole? Can we unify quantum mechanics and general relativity? Is there a limit to how much information can be stored in matter? Do black holes destroy information, or do they somehow preserve it in hidden ways? All of that could come from watching one rogue black hole devour one neutron star. That's the power of these collisions. They're like keys to the universe. And they're drifting out there in the dark, waiting for us to notice. But what it really means is this: when a neutron star gets torn apart by a black hole, it literally forges gold, platinum, uranium, some of the rarest materials in existence. The very atoms in your jewelry or in nuclear reactors might have come from an event like this. Think about that for a second. A violent collision between a rogue black hole and a neutron star, somewhere billions of light years away, could have seeded our solar system with the heavy elements that eventually became part of Earth. So when we say, "We are made of stardust," it's not just poetry, it's physics. These events are the cosmic furnaces that shaped our material world. Without them, the periodic table would be missing its most precious elements. And Earth, as we know it, might not even exist. Now, let's talk about how scientists even begin to detect or predict these kinds of events. Because we're not just guessing here. We're building models, running simulations, and comparing them with the real signals we receive from space. One of the biggest challenges is that black hole, neutron star mergers are rare. Really rare. We've only confirmed a couple so far through gravitational wave detections. But the ones we've found already challenge what we thought was possible. In one case, the black hole was so small and the neutron star so dense that scientists weren't sure which one was which at first. In another, the merger left behind no electromagnetic signal, no light, no gamma ray burst, just the quiet tremor of a space-time ripple that said, "Something massive just happened." This silence is part of the mystery. Some collisions create bright flashes. Others are completely dark. Why? Is it the angle we're looking from? The speed of the impact? The mass ratio? We don't fully know. But each new detection adds a puzzle piece. And that's why astrophysicists are obsessed with finding more of them. Every time one of these rare mergers happens, it's like the universe giving us a brief peek behind the curtain. A glimpse of the hidden engine room powering the cosmos. And rogue black holes make that engine even more unpredictable. Because unlike black holes in binary systems, rogue black holes don't follow a pattern. They don't stay in one place. They don't play by any rules. They could be drifting through the outskirts of galaxies or gliding through intergalactic space with nothing but darkness around them. That makes them almost impossible to detect, until they crash into something. And neutron stars, despite being dense and energetic, are tiny targets in a vast ocean of emptiness. That's why these collisions are so rare. But when they do happen, they're like cosmic jackpot events. One hit can reveal more about physics than a decade of observation. And here's the wild part. Some scientists think these rogue black hole, neutron star collisions might happen more often than we currently believe. We just can't see them. Think about it. If a merger doesn't release any light, and if the gravitational waves are too faint, or the detectors on Earth aren't sensitive enough to catch them, then it's like it never happened. It's invisible. Silent. Gone. Which raises a chilling question. How many of these cosmic collisions are happening right now, in this very moment, and we have no idea? Imagine millions of galaxies, each with billions of stars. Now imagine thousands of neutron stars left behind after supernovae, drifting in the outer reaches of those galaxies. Add to that an unknown number of rogue black holes kicked loose from their orbits by past mergers or gravitational slingshots. It's not just possible that they're colliding, it's likely. Somewhere, out there, two of the most extreme objects in the universe are spiraling toward each other right now. No one will see it. No one will hear it. But the universe will feel it. Cutting straight through them like bullets in slow motion. They might pass close to star systems, warp planetary orbits, or pull in lone neutron stars like magnets catching bits of metal. And because they don't have companion stars feeding them a steady stream of matter, they stay invisible most of the time. Completely undetectable except through the occasional flicker of gravitational lensing or the gravitational waves they emit when something catastrophic happens around them. That unpredictability is what makes them so fascinating, and so terrifying. We have no idea how many of them are out there, what paths they're on, or how close they might ever come to us. Now imagine this happening not just once, but millions of times across the universe. Entire neutron stars getting consumed. Whole regions of space warped by traveling black holes. Mergers flinging debris across galaxies. Some of that debris may eventually condense into new stars, maybe even planets. Other pieces might be launched into interstellar space at insane velocities, becoming lone travelers themselves. Every event like this reshapes the structure of the universe in tiny, invisible ways. And most of it goes on without us even knowing. That's the humbling part. We think of space as this vast, quiet void, but underneath that stillness is chaos. A slow, grinding, relentless chaos driven by gravity, motion, and time. And what happens when the black hole wins? What's left after the neutron star is completely devoured? Well, the black hole gets bigger. That's it. No light show. No fireworks. Just more mass added to the darkness. And maybe that's the scariest part. It just keeps growing. Slowly. Silently. Adding to itself with every meal. In the grand scale of the universe, these little mass additions can lead to monsters. Rogue black holes can eventually become intermediate mass black holes, or even supermassive black holes if they feed enough. And when they collide with other black holes, the process continues. It's like cosmic evolution, survival of the hungriest. But here's something most people don't realize. When a neutron star gets close to a black hole, the collision isn't instant. The neutron star might orbit the black hole several times before it's destroyed. Each orbit stretches it, pulls it, deforms it. It's like watching a rubber ball get squeezed tighter and tighter until it bursts. That process can create tidal disruption events, bursts of energy that last seconds or even minutes. And in those seconds, we might be able to see the light, the heat, and even the gravitational waves from the struggle. But you have to be looking in just the right direction, at just the right time, with the right equipment. Otherwise, it's gone before you even know it happened. And the technology we use to catch these moments is getting better every year. LIGO and Virgo, the gravitational wave detectors, are constantly scanning space for the tiniest ripples. Future detectors like the Einstein telescope and LISA, the laser interferometer space antenna, will be able to sense even weaker signals from farther away. That means in the coming decades, we might detect dozens, maybe hundreds, of these black hole, neutron star mergers. Each one giving us new data, new clues, and new mysteries to solve. But there's another layer to this that's even more chilling. Some scientists have proposed that rogue black holes might pass through regions where stars are densely packed, like globular clusters or galactic cores. In those crowded neighborhoods, the chance of collision is much higher. You could have multiple neutron stars, white dwarfs, even main sequence stars, all orbiting each other, and then, bam, a rogue black hole sweeps through. It's like throwing a bowling ball through a room full of spinning plates. The aftermath is pure destruction. Star systems get ejected. Mergers happen. Everything changes in seconds. These rogue interactions could be shaping the architecture of galaxies without us ever seeing the cause. And if that's true, then rogue black holes aren't just cosmic scavengers, they're architects of change. Sculptors of space. Their movements, collisions, and gravitational influence might be driving the evolution of entire galactic regions. And yet, we can't see them. Can't track them. Can't stop them. We only know they're out there because we see the scars they leave behind. Disrupted stars, gravitational waves, and the sudden appearance of elements that could only be formed in the most extreme conditions imaginable. Finally snaps. And when it does, the force unleashed is beyond anything we can replicate or fully grasp. Tidal disruption happens. The neutron star is literally torn apart by the gravity of the black hole. The material of the neutron star, once compressed so tightly it was almost pure neutrons, is ripped into a swirling disk of plasma. This disk spins at near light speed, glowing hot, emitting X-rays and gamma rays as it spirals in. For a few brief moments, it becomes one of the brightest objects in the universe. Then, just as suddenly, the light dies. Everything is gone, swallowed by the singularity. This is one of the most extreme endings any object in the universe can experience. But it's also a beginning in disguise. Because the material flung outward by the disruption doesn't always fall in. Some of it escapes. And this escaping matter carries signatures, signals, that scientists can detect. By studying the electromagnetic radiation, the gravitational waves, and even the neutrinos that are shot out during the collision, researchers can reverse engineer what happened. They can figure out how fast the objects were moving, how massive they were, even what they were made of. That's why these events are so valuable scientifically. They're like time capsules from the deep cosmos, filled with data that tells us how the universe works at its most violent edges. And don't think this is just theory. We've already seen some of this in action. In August 2019, the LIGO and Virgo gravitational wave observatories picked up a signal that looked exactly like a black hole, neutron star merger. It was named GW190814. But here's the twist. The objects involved didn't behave like we expected. One of them was clearly a black hole, but the other wasn't heavy enough to be a typical black hole, and wasn't light enough to be a typical neutron star. It was right in between. This freaked scientists out, because it suggested the existence of a whole class of objects we've never observed before. Something in that mass gap between neutron stars and black holes. Was it a super-heavy neutron star? A miniature black hole? Something new entirely? This is what rogue encounters do. They break our models. They challenge our neat little categories. Every time we think we've mapped the rules, the universe throws in a curveball. And rogue black holes, by their very nature, are curveballs in motion. They don't belong to star systems. They don't orbit galaxies in neat spirals. They're outliers. Loners. Rule breakers. And when they meet something as exotic as a neutron star, the result isn't just a merger, it's a revelation. A discovery. A reshaping of what we think we know. Now let's go even deeper. One of the wildest possibilities is that some of these neutron stars might actually be something even stranger. Quark stars. That's right. Inside neutron stars, if the pressure becomes high enough, the neutrons themselves might break down into their constituent parts, quarks. That would create an object even denser than a neutron star, something we've never observed directly. If a rogue black hole were to collide with a quark star, the explosion could release physics we've never seen before. Particles we've never detected. Forces that only existed in the first seconds after the Big Bang. That's why astronomers are desperate to catch more of these events. Every black hole, neutron star merger could be a hidden quark star detection. Every gravitational wave could be a clue to the nature of matter at the smallest scale. It's a weird twist, but these cosmic catastrophes might hold the secret to understanding the tiniest pieces of our reality. In other words, to understand the subatomic world, we have to look at the most massive, violent events in the cosmos. That's the irony. The key to the smallest things is hidden in the biggest things. They might be the biggest curveball of all. Think about it. These are objects that have no fixed location, no predictable pattern, no companions to help us find them. They don't shine, they don't reflect, they don't emit anything we can easily detect unless something gets too close. And there could be millions of them, scattered across our galaxy and beyond. Each one a cosmic predator, silently drifting through the darkness. Some of them could be as small as a few solar masses, others could be ancient black holes from the early universe that have been wandering alone for billions of years. No one knows where they were born, or where they're going. And that's the truly terrifying part. A rogue black hole could be heading straight for us right now, and we wouldn't see it coming until it started pulling on our solar system's outer edges. Now, what makes things even more complex is that neutron stars themselves are already among the most extreme things in existence. Just a single teaspoon of neutron star matter would weigh over 1 billion tons. These are the collapsed cores of massive stars, remnants of supernova explosions where gravity was so intense that protons and electrons fused into neutrons. What's left is a star the size of a city but heavier than the Sun. The magnetic fields are trillions of times stronger than Earth's. The surface temperature can reach 1 million degrees. And some neutron stars spin hundreds of times per second, sending out beams of radiation like cosmic lighthouses. They're basically stellar corpses with superpowers. So when something that extreme runs into a rogue black hole, the result isn't just destruction, it's transformation. It's a complete rewriting of local space. The fabric of space-time itself bends, stretches, and ripples as gravitational waves are launched outward. And these waves don't just travel, they carry energy across the universe. When LIGO detects a wave from one of these collisions, it's actually detecting a tiny ripple in the Earth itself, less than a fraction of the width of a proton. That's how sensitive this stuff is. That's how deep these events reach. They shake the universe so hard that the vibration crosses billions of light years, and we can still feel it. And then there's the question of what's really happening inside these neutron stars. Before they're destroyed, they offer a unique laboratory for physics. We don't fully understand the state of matter inside them. Is it all just neutrons? Or is there something deeper, like quark matter, where particles are broken down into even more fundamental components? Some theories even suggest exotic states of matter like strange matter, or quark-gluon plasma. These are conditions that can't be replicated on Earth, even in our most powerful particle colliders. But in the final seconds before a neutron star is shredded by a black hole, all that inner matter is exposed. For a brief moment, we get a glimpse of what lies at the deepest level of physical reality. And this might even tie into dark matter, one of the biggest mysteries in the universe. There's a theory that some of the matter ripped from neutron stars could transform into dark matter under certain extreme conditions. If true, these black hole, neutron star collisions wouldn't just be rare events. They'd be factories for the mysterious substance that makes up most of the universe. That's a huge leap, but it shows just how deep this rabbit hole goes. The more we learn, the more it seems like these events aren't just random space explosions. They're central to how the universe builds itself, recycles itself, and evolves. But maybe the most mind-bending part of all this is the question of what happens inside the black hole after it eats the neutron star. According to general relativity, all the mass just adds to the singularity, a point of infinite density. But that's not the end of the story. Quantum physics disagrees. It says that information can't be destroyed. So what happens to all the data inside that neutron star? All its structure, energy, motion? If it just vanishes into the singularity, that would break the laws of quantum mechanics. This leads to one of the biggest unsolved questions in physics, the information paradox. And these mergers might be the key to solving it. Because when matter falls into a black hole, it emits radiation, Hawking radiation, to be exact. And there's a theory that this radiation carries the lost information, scrambled and stretched across the event horizon like a cosmic barcode. If we could understand exactly how that works, how the information of a destroyed neutron star gets encoded into a black hole, we'd be cracking open the code of the universe itself. We'd finally bridge the gap between relativity and quantum mechanics. And that's the holy grail of physics, a unified theory of everything. So these seemingly rare, hidden collisions out in the far reaches of the cosmos, they might hold the answers to questions we've been asking for centuries. What is space? What is time? What is matter? What is reality made of? And we're only just beginning to see the surface. Every time a new wave hits our detectors, every time a new signal flashes across the sky, we're learning more. And yet the universe keeps its biggest secrets buried in silence, tucked away in corners we can't see, guarded by these silent travelers, rogue black holes with no name, no light, no home. Just endless hunger, drifting in a sea of stars. Matter inside a neutron star. It's not just dense, it's a kind of matter that doesn't exist anywhere else in the universe, at least not that we can recreate. Scientists believe that deep inside, past the crust and the layers of neutrons, there might be something even stranger, quark matter. This would be a state where neutrons themselves break apart into their most fundamental components, quarks, and maybe even form something called a quark-gluon plasma. That kind of matter might have existed only in the earliest moments after the Big Bang. But inside a neutron star, under unimaginable pressure, it could still exist today. And here's where it gets even crazier. If a rogue black hole collides with a neutron star, and we manage to detect the resulting waves and radiation, we might finally have a way to confirm what's going on inside these mysterious stellar cores. Imagine that. Two of the strangest, most powerful objects in the universe smashing into each other, and in that moment of destruction, giving us clues about the beginning of everything. That's why scientists are obsessed with tracking these events. Every collision is like a physics experiment on a scale we could never build ourselves. And these aren't rare freak accidents either. In just a few years since gravitational wave detectors became sensitive enough, we've already found dozens of these events. And we're just getting started. The more detectors we build, and the more sensitive they become, the more of these rogue collisions we'll uncover. But there's another angle to all of this that makes it even more mind-blowing. Rogue black holes don't just mess with stars, they mess with time. When anything gets close to the event horizon, the invisible boundary around a black hole, time itself slows down. To an outside observer, it would look like the neutron star is being stretched and frozen in time as it falls in. But from the neutron star's own perspective, everything continues normally until the very end. This isn't science fiction. This is Einstein's general relativity, and it's been confirmed again and again. So when we talk about a rogue black hole merging with a neutron star, we're also talking about a breakdown of our everyday understanding of time and space. What does it feel like to fall into a black hole? What happens to information? Can anything escape? These are questions physicists are still debating today. And all of that loops back to one core idea: the universe is far wilder than we ever imagined. We used to think it was static, orderly, predictable. Now we know it's full of silent threats and unseen events playing out across billions of light years. Rogue black holes are a perfect symbol of that chaos. They don't follow rules. They don't orbit stars. They don't form neat binary systems we can model and study. They wander, they collide, and they change everything they touch. And the truly mind-bending part? We're just scratching the surface. What if there are other kinds of black holes we haven't even theorized yet? Primordial black holes from the early universe? Tiny micro black holes that evaporate in bursts of energy? What if the collisions we've seen are only a small part of the total story? What if rogue black holes are doing things out there that don't even create signals we can detect yet? The universe is dark and full of mysteries. Rogue black holes merging with neutron stars is just one terrifying, beautiful, violent chapter. And the more we learn, the more we realize how little we truly know. Back to one chilling possibility. These rogue black holes could be erasing entire neutron stars from the universe without a trace. Think about that. These collisions could be happening all the time, all over the cosmos, but unless we're watching at the exact right moment, with the exact right tools, we'll miss it completely. No light, no signal, just a star that vanishes, consumed by something that doesn't even leave behind a glow. And that raises the possibility that we might be underestimating how many rogue black holes are really out there. The ones we detect might just be the tip of the iceberg. If we miss the ones that don't emit detectable radiation, if we miss the ones that don't shake the universe quite hard enough for us to feel it, then we're blind to a huge part of what's happening in the dark. And here's something even more haunting. There's growing evidence that some rogue black holes are ancient. Like really ancient. Possibly older than the galaxies themselves. These primordial black holes, as they're called, might have formed in the chaos just after the Big Bang. They might be smaller than stellar mass black holes, but far more numerous. Some theories even suggest that these early black holes might be part of what makes up dark matter, the mysterious substance that seems to hold galaxies together but doesn't interact with light. If even a fraction of dark matter turns out to be made of rogue black holes, then the universe is way more dangerous and unpredictable than we ever thought. Now let's bring this back to neutron stars. These aren't just dead stars, they're also time bombs of information. Their structure holds clues about nuclear forces, about gravity, and about the fundamental behavior of matter under pressure that we can't replicate anywhere else. If a rogue black hole swallows a neutron star before we get a chance to observe it, we lose all of that. We lose the chance to decode how the universe behaves under its most extreme conditions. And that's why astronomers are racing to develop better telescopes, better detectors, and better algorithms to catch these events as they happen. Some scientists are working on next-generation gravitational wave observatories, massive underground detectors, space-based observatories like LISA, and even projects that use pulsars as a sort of galactic microphone, listening for ripples in spacetime across the Milky Way. These tools will help us pinpoint where and when these collisions occur, and maybe even catch the exact moment a neutron star is torn apart. With enough data, we could finally start answering the big questions. What's inside a neutron star? How do black holes form and evolve? What role do they play in shaping galaxies? And most importantly, how common are these rogue encounters? But here's a twist. Some of these collisions might not end with just one winner. In rare cases, if the neutron star is massive enough and the black hole is relatively small, there's a theoretical possibility that a temporary disk of matter forms around the black hole. This disk heats up, glows brightly, and can launch jets of radiation at near light speeds. That's what we call a short gamma-ray burst. It only lasts a few seconds, but it can outshine everything else in the sky while it happens. These bursts are like cosmic flashbulbs, brief, intense explosions that let us peek into the moment of impact. Some of the brightest gamma-ray bursts we've detected could very well be the result of a rogue black hole devouring a neutron star. And then there's the matter of where these events happen. A lot of people picture them happening in dense star clusters or the cores of galaxies. But rogue black holes don't follow that rule. They can drift into the outskirts of galaxies, into the vast voids between stars, or even into deep intergalactic space. They're wanderers, free from any gravitational anchor. That means some of the most intense, violent collisions in the universe might be taking place in complete isolation, far from anything else. No nearby stars, no galaxies to light up the scene, just a neutron star and a black hole meeting in the middle of nowhere. And if you want to get really wild, think about this. Some scientists believe there could be rogue black holes in our own galaxy, not just drifting through space, but quietly moving through the Milky Way's disk. One could be passing through the outer reaches of our solar system right now, completely undetectable. If it got close enough, it could disrupt the orbits of comets in the Oort cloud, potentially sending a rain of icy debris toward the inner solar system. And if it got even closer, well, we're talking about the kind of gravitational chaos that could end worlds. This isn't likely to happen anytime soon, of course. But the fact that it's possible? That's enough to keep scientists looking over their shoulders. Because the universe doesn't play favorites. Now zoom out for a second and look at the big picture. These rogue black holes and neutron star collisions aren't just cool, rare cosmic events. They're part of the engine of the universe. Every time a neutron star gets ripped apart, heavy elements like gold, platinum, and uranium are created. These elements get flung into space, scattered across galaxies, and eventually become part of planets, and even us. The gold in your jewelry, the uranium in a reactor, the rare elements in your smartphone, there's a real chance they were born in the aftermath of a neutron star being destroyed by a black hole. That's how connected everything is. The most violent collisions in the universe are part of the reason life exists at all. And the more we look, the more we realize how little we actually know. We used to think black holes were just endpoints. The death of stars. But now we're learning they're also creators, shaping galaxies, creating elements, and rewriting the rules of physics. And the rogue ones? They're the outlaws of the cosmos. No pattern. No warning. Just silent gravity, creeping across the universe, ready to erase anything in their path. And when one of them finds a neutron star, a spinning core of dead matter still pulsing with energy, the collision is like the final act of a cosmic drama. One that ends in silence. In darkness. In a black hole just a little bit bigger than before. These new tools will give us sharper ears and clearer eyes to detect the silent roars of space. Things like a rogue black hole quietly ripping a neutron star apart in some far-off galaxy. And what's wild is that these events aren't just isolated to deep space. Rogue black holes could be passing through our own galaxy right now. We might not even know it. If one is truly rogue, if it has no accretion disk, no star to feed on, no light to reveal it, it's basically invisible. The only sign might be gravitational lensing, where the black hole warps the light from stars behind it, like a magnifying glass sliding across the sky. In fact, scientists are using this method to try and count how many rogue black holes might be wandering through the Milky Way. It's like looking for invisible landmines floating in space, quiet, dark, but capable of destroying everything in their path. And think about how close they could get. If a rogue black hole were to drift into our solar system, not even collide, just pass through, it could fling planets out of orbit, bend the path of comets, and potentially send Earth into chaos. And we probably wouldn't know until it was too late. That's not fear-mongering, it's just gravity. That's how powerful these things are. They don't even need to touch something to ruin it. And when they do collide, especially with neutron stars, the result is one of the most violent, dramatic events the universe has to offer. The forces involved are off the charts. We're talking about matter being torn apart at the atomic level, magnetic fields 1 trillion times stronger than Earth's, and temperatures hotter than anything in the core of a star. The gravitational waves released in those moments travel across space at the speed of light, shaking the very fabric of reality as they go. And we've only just started learning how to listen to them. Gravitational wave astronomy is barely a decade old, but it's already rewriting everything we thought we knew. In 2017, scientists detected a neutron star merger for the first time and watched it light up in multiple forms of radiation, X-rays, gamma rays, visible light. It confirmed theories about where heavy elements like gold and platinum come from. It opened a window into nuclear physics. And it gave us a glimpse of what might happen when a neutron star and a black hole merge. But we've only scratched the surface. Most of these events are still shrouded in mystery. We don't know how common neutron star, black hole collisions are. We don't know how often rogue black holes are responsible. And we don't know what kind of exotic physics might be hiding in those final moments before the two objects merge. Some theories go way beyond what we can currently prove. There are hypotheses that say inside a neutron star, matter could become so compressed that it forms a kind of superfluid, matter with zero viscosity that can flow without resistance. Others suggest that if you compress matter hard enough, you might get strange quark matter, stuff so dense and stable that it could survive even the chaos of a merger. And then there's the idea that these collisions might form something entirely new, a magnetized hybrid object, or even a brief, unstable star made of pure quarks before it collapses into a black hole. These aren't just thought experiments. They're possibilities that real physicists are actively studying. And every time we detect a new gravitational wave signal, we get a little closer to knowing what's real and what's not. The coolest part? You don't need a spaceship to witness any of this. These events happen millions of light years away, but they still touch us. The ripples in space-time, the bursts of light and radiation, they travel across the cosmos and arrive here, on Earth, sometimes after billions of years. We're literally listening to ancient violence, playing out in slow motion across the stars. And it all ties back to rogue black holes. These silent drifters, these cosmic phantoms, are the key to unlocking a part of the universe we still barely understand. They're the missing players in a cosmic drama that's been unfolding since the beginning of time. Every time they collide with a neutron star, they don't just destroy something, they tell us a story. And we're finally learning how to read it. A rogue black hole meet in the dark. But here's the thing, when a black hole and a neutron star collide, the result is usually silence. Sometimes we don't get the fireworks. Sometimes, the black hole is so massive and the neutron star so small that the whole thing ends in a whisper. The neutron star gets swallowed whole before it has a chance to emit any light or leave behind any trail. This is called a dark merger, and it's one of the eeriest possibilities in astrophysics. We only know these happen because of the faint tremor they send across spacetime, gravitational waves that we're just now beginning to detect. No flash, no burst, no gamma-ray beacon. Just a ripple that tells us something happened, and it was big. And that's what's so crazy. The biggest, most powerful events in the universe might be the quietest. These dark mergers are like perfect crimes. The neutron star, one of the densest, most extreme objects in existence, gets erased in a split second, and the universe keeps moving like nothing happened. If our instruments weren't tuned just right, we wouldn't even know it occurred. Now think about how many of those we've missed over the years. Every silent collision is a lost opportunity to learn something new about gravity, about matter, about the evolution of stars. Now let's talk about what actually happens during one of these collisions. When a neutron star merges with a black hole, the outcome depends heavily on two things: the mass of the black hole, and the mass and structure of the neutron star. If the black hole is small, say, just a few times the mass of our Sun, and the neutron star is on the heavier side, there's a chance that the neutron star gets torn apart before it falls in. And when that happens, we get a show. Matter from the neutron star gets flung outward at near light speeds. This matter is extremely neutron-rich, and when it decompresses, it undergoes rapid neutron capture, a process called our process nucleosynthesis. That's a mouthful, but here's the simple version. It creates the heaviest elements in the universe. Gold, platinum, uranium. Stuff that doesn't come from stars in their normal life cycle, but only from their violent deaths. That's where your wedding ring came from. That's where the metal in your phone may have come from. It's not just stardust, it's neutron stardust, flung out during one of the most extreme collisions in existence. But when the black hole is too massive, it just swallows the neutron star whole. No debris. No light. No gold. Just gravitational waves and silence. And here's the wild part. We think the majority of these mergers probably fall into that second category. So most of the universe's neutron stars might not even get the chance to leave a trace. They might just disappear into a rogue black hole like they never existed. And we don't know where those black holes go after that. A black hole that merges with a neutron star usually becomes more massive. It gains energy. It warps space around it even more intensely. Some might even get kicked out of their home galaxy entirely. Yeah, you heard that right. These objects can be launched into intergalactic space, moving at millions of kilometers per hour. Imagine a massive, invisible black hole carrying the corpse of a neutron star, just flying through the void between galaxies. It's the ultimate cosmic ghost ship, silent, unstoppable, and completely hidden. What's even more terrifying is how common this might be. The Milky Way alone may contain over 100 million black holes, most of them unaccounted for. A significant fraction could be wandering through space, unbound by any star system. Some might have formed from dying stars. Others could be primordial, as we mentioned earlier. But no matter where they come from, the fact remains, they're out there. And neutron stars, which are already rare and strange to begin with, are constantly at risk of becoming their next meal. And it doesn't stop there. Some theories suggest that when a neutron star gets too close to a black hole, even before they merge, weird things start to happen. The neutron star's crust might crack under tidal forces, releasing bursts of gamma radiation. It might even start shedding its magnetic field, spraying charged particles into space. These events could look like fast radio bursts, those mysterious signals we sometimes detect from deep space, lasting only milliseconds. We don't know where they come from. But one theory is that they're coming from neutron stars being torn apart by rogue black holes. So the next time we detect a burst like that, it might not just be a random pulse. It might be the death scream of a neutron star that's just been devoured. And here's where it gets philosophical. When a neutron star merges with a black hole, we lose something that's not just scientifically important, it's emotionally profound. Neutron stars are born from supernovae, the deaths of massive stars. They're survivors. They're remnants of some of the most powerful explosions in the universe. And they hold within them the memory of that event, the structure of their core, the shape of their magnetic field, the speed of their rotation. All of it tells a story. When a black hole swallows a neutron star, that story ends. It's like a book being thrown into a fire. All the information inside, the data, the history, the complexity, gets lost. Some scientists believe that information is never truly destroyed, not even in a black hole. But we don't know. And until we do, every silent merger feels like a chapter ripped out of the universe's history, burned before we could read it. What we're witnessing with these collisions isn't just destruction, it's transformation. It's the universe reshaping itself, one violent event at a time. And every time it happens, we get a little more insight into how everything fits together. Matter, gravity, space, time, it all comes into focus in those moments of cosmic violence. And while rogue black holes and neutron stars might seem like rare, distant objects, they're actually teaching us something about the most fundamental rules that govern reality. Where every speck of gold on Earth was born, from ancient, cataclysmic collisions between dead stars and the invisible monsters that roamed the universe. It wasn't mined into existence, and it didn't slowly form in the furnace of a star. It came from destruction on a scale so massive it shook the universe itself. When we say, "You're wearing a piece of a neutron star," it's not just poetic, it's literally true. The debris flung out from those mergers travels through space, cools over time, and some of it ends up in the dust clouds that eventually become solar systems. Planets. People. That means we're not just made of stardust, as the old saying goes. We're made of collision dust, the remnants of stars ripped apart by black holes. But that's only one possible outcome. Because if the black hole is too big, too heavy compared to the neutron star, then there's no debris. No elements. No fireworks. The black hole simply swallows the neutron star whole like a cosmic vacuum cleaner. This is what we think happens in a lot of these events. And for years, that's why they went unnoticed. Because they didn't light up the sky. They didn't create a flash of X-rays or a blast of gamma rays. They didn't even leave behind enough matter to form a disk. They just disappeared. But now that we can detect gravitational waves, we can hear them happening. These waves don't care about light. They don't need a telescope. They just ripple through space and stretch everything in their path, even if only by a fraction of a proton's width. And our instruments, like LIGO and Virgo, are sensitive enough to catch those faint murmurs from across the universe. One of the most mysterious parts of all this is how rogue black holes, ones not tied to any star system, come into play. Most black holes we've studied are in binaries. They orbit another star, feeding on it, occasionally flaring up when the gas heats up and gives off X-rays. But rogue black holes are loners. They drift through space after being kicked out of their original systems, maybe after a supernova explosion threw them loose. And here's where it gets fascinating. If a rogue black hole happens to pass close to a neutron star that's already on its own, they could get caught in each other's gravity and slowly spiral in. No warning. No bright light. Just a dark dance ending in silence and gravity. We suspect these events happen more often than we thought. In fact, some scientists believe there could be millions of rogue black holes just in the Milky Way. They don't glow. They don't orbit anything. But if you were close enough, you'd feel their gravity. You'd feel everything get warped. Time would slow down. Light would bend. Space would twist. You wouldn't be able to see it with your eyes, but you'd know something was off. And if it collided with something else, like a neutron star, it would trigger a ripple that spreads out in all directions. A gravitational wave. And what's terrifying is how unpredictable these rogue black holes are. We can't track them. We don't know where they're headed. They could pass through a solar system, scatter planets like marbles, and keep going. If one ever drifted through our solar system, we might only notice after Earth's orbit starts changing, or worse. But even without touching us, they can cause chaos across space. If a rogue black hole collides with a neutron star near us, say, in our galactic neighborhood, the gravitational waves could be strong enough to be clearly detected. And with our growing global network of detectors, we'd be able to triangulate where it happened and how massive the objects were. That gives us clues not just about the event, but about what's out there that we can't see. The idea that space is filled with these invisible monsters, black holes with no stars, no light, just gravity, is one of the most unsettling and exciting truths in modern astronomy. And as our technology improves, we're starting to see patterns. We're noticing differences between neutron star mergers, black hole mergers, and black hole, neutron star mergers. The signals are different. The energy is different. The aftermath is different. And maybe the most important detail of all? Some of these events leave behind nothing. No disk. No jets. Just a silent increase in the mass of a black hole, and a gravitational whisper that says, "Something just ended." And the more we detect, the more we realize just how violent the universe really is. Space isn't calm. It's not quiet. It's a war zone of massive objects tearing each other apart. And rogue black holes are like the snipers. You don't see them coming, and they strike without warning. And neutron stars? They're like walking time bombs, stable for a while, but waiting for the wrong encounter. When these two meet, it's not just death, it's transformation. Elements get made. Light gets twisted. Space gets warped. And the universe adds another ripple to the story we're only just beginning to understand. Drifting alone, maybe after a similar stellar explosion, it could set off a merger that no one saw coming. No orbit, no slow spiral, just a straight-up collision. Two ancient remnants from the death of stars, colliding like wrecking balls in the middle of nowhere. And since rogue black holes don't give off light, and lone neutron stars are incredibly hard to detect unless they're pulsars, we probably wouldn't see the merger coming at all. There'd be no warning, no glowing prelude, just an unexpected gravitational wave signal, maybe with no light to follow it. Scientists would scramble to point telescopes at the spot, hoping to catch a flash. But in most cases, there might be nothing. Just a brief ripple in the fabric of the universe, and then silence. But don't mistake silence for simplicity. These mergers, especially between a rogue black hole and a neutron star, are some of the most complex phenomena out there. The physics is extreme. The neutron star is already an exotic object, just a few kilometers across, but with more mass than the Sun. Its surface gravity is so strong that if you dropped a paperclip from a meter above, it would hit with the force of an atomic bomb. Its interior is made of ultra-dense nuclear matter, possibly even quark matter, something we've never been able to recreate on Earth. And when it starts to get torn apart by the tidal forces of a black hole, things get crazy. Matter gets stretched into long streams, like spaghetti, and if the black hole isn't too massive, These streams can escape its pull and spiral outwards, forming a glowing accretion disk. That disk is key. It can light up the merger in gamma rays or X-rays. It can fuel a relativistic jet, a narrow beam of particles moving at nearly the speed of light. These are the famous gamma-ray bursts we sometimes catch with our space telescopes. And when we do, it tells us that a neutron star just died in the most violent way imaginable. But here's the twist. We still don't fully understand what conditions are required for those jets to form. Sometimes we get a merger and no jet. Other times, a small flash. Every event is different. And we're only beginning to build a catalog. And while we're on the topic of rogue black holes, let's not forget, they're almost completely invisible. The only reason we even know they exist is from the way they bend light behind them, through a process called gravitational microlensing. If a rogue black hole passes in front of a distant star, its gravity warps the light coming from that star and causes it to brighten temporarily. It's a tiny effect, and you have to be looking at the right place at the right time to catch it. But it's happened. And it confirms something chilling. Our galaxy is likely full of these silent, invisible objects, drifting alone through the dark. And if just one of them gets close enough to a neutron star, well, you know what happens. But here's the deeper mystery. How often do these collisions actually occur? That's one of the hardest questions in astrophysics right now. LIGO and Virgo have detected a few neutron star, black hole mergers, but only a handful. Are these events rare? Or are they just happening in ways we can't detect? Too far, too dark, too quiet? Maybe we're missing most of them. Maybe rogue black holes are responsible for more cosmic evolution than we realize. Some scientists think these collisions could be one of the main ways black holes grow over time, consuming neutron stars like snacks as they drift through the galactic halo. It's like a hidden ecosystem of dead stars, playing out on timescales of billions of years, mostly out of sight. And that brings us to something even weirder. What if the black hole doesn't completely destroy the neutron star? What if, somehow, some piece of it survives the merger? This is purely theoretical, but some physicists have speculated that in rare cases, the core of the neutron star might be compact enough to fall into the black hole without getting torn apart, and that it might remain intact, at least for a moment. That sounds impossible, but we're dealing with physics at the edge of what we understand. If that happens, it might mean strange new kinds of matter, or even exotic states of spacetime that defy our current models. Now, take all this and stretch it across cosmic time. Think about how many billions of stars have died since the universe began. How many neutron stars have been born in supernova explosions? How many of those have wandered alone through space? How many rogue black holes have formed, and how many are out there right now, invisible to our telescopes, just waiting to collide with something dense enough to create a ripple in space-time? We're probably talking about millions of these events in the history of the universe. Maybe more. And we've only just started listening. So, where does that leave us? At the beginning. That's the crazy part. Even after detecting a few neutron star, black hole mergers, we're still in the opening chapter. We're just starting to understand what kinds of objects are out there, how they die, and what happens after they do. Rogue black holes, neutron stars, dark mergers, all of these are pieces of a puzzle that stretches across the whole sky. And for every event we catch, there are probably thousands we miss. The universe is whispering secrets through gravitational waves. And now, finally, we're learning to hear them. Impossible to find unless they interact with something. A rogue black hole doesn't shine, doesn't radiate, and doesn't reveal itself, unless it starts to mess with its environment. That might mean lensing the light of a star behind it, or sucking in gas and making it glow in X-rays, or, more dramatically, crashing into a neutron star. Otherwise, these black holes are just ghosts drifting through space. And there could be millions of them in our galaxy alone. Some estimates say there may be as many as 1 billion stellar mass black holes in the Milky Way, and most of them would be completely invisible. Just silent monsters lurking between stars. Now think about this. If even a small fraction of those rogue black holes occasionally run into a neutron star, that means there are likely way more of these collisions happening than we've ever detected. We're only scratching the surface. And if we could hear all of them, the ones with no light, no flare, just gravitational waves, we'd be overwhelmed by how many times the universe is smashing these ultra-dense objects together. It makes you wonder, how much of the universe's heavy elements come from these kinds of mergers? How many black holes are roaming out there, gobbling up neutron stars before anyone knows they exist? How many mystery gravitational wave signals we've recorded already might have been rogue black hole mergers, and we just didn't know? Even stranger, some scientists speculate that a certain kind of merger, where a black hole swallows a neutron star whole without a trace, might be how some intermediate mass black holes form. These are the missing link black holes, heavier than stellar mass ones, but smaller than the supermassive giants at the centers of galaxies. We've seen hints of them, but they're rare. And one theory says they might build up from these very events, one neutron star at a time, like cosmic cannibals eating their way to greatness. Over billions of years, a rogue black hole could consume several neutron stars, growing larger each time, until it becomes massive enough to count as intermediate. It wouldn't shine. It wouldn't flash. But it would grow, one bite at a time. And now imagine one of those rogue black holes, headed in our direction. No light. No sound. Just an invisible bullet flying through the galaxy. Would we even know it until it was too late? Probably not. Gravitational wave detectors aren't directional enough yet to track one coming in real time. Our best hope would be gravitational lensing, where the black hole distorts the light of stars behind it, briefly magnifying them. That's how we've spotted some candidates. But the odds of catching one in the act are slim. Which means a rogue black hole merging with a neutron star isn't just a cosmic mystery, it's a silent threat. A rare but real possibility that makes the universe feel a little less safe. And there would be no way to see it coming. That's the terrifying beauty of rogue black holes. They don't announce their arrival with explosions or flares. They don't give us bright tails or glowing markers to trace. They simply move, dark, silent, and relentless. A rogue black hole moving through interstellar space at a few hundred kilometers per second could cross the vast distance between stars in just a few million years. That might sound like a long time, but in galactic terms, it's nothing. And if one were headed toward our solar system? We probably wouldn't know until it started disrupting the outer edges of the Oort cloud, scattering comets and asteroids in unpredictable ways. Even then, we might not realize the true cause. Until gravity started to shift. Until orbits started to bend. Until the planets, ever so slightly, began to drift. But here's the thing, even if a rogue black hole never comes close to us, they are already affecting the structure and fate of galaxies. When these objects roam the dark, they interact with dark matter halos, they shape stellar populations by disrupting binary systems, and they influence the long-term dynamics of star clusters. We're learning that rogue black holes aren't just leftovers of stellar deaths. They are dynamic players in the cosmic ballet, pushing and pulling matter in ways we're just beginning to understand. And when one merges with a neutron star, which is itself one of the most extreme states of matter, the result is a kind of cosmic alchemy. A process so violent and strange that even Einstein's equations struggled to keep up. Inside that neutron star is matter at nuclear densities. A single teaspoon would weigh 1 billion tons. The atoms are crushed so tightly that electrons and protons have fused into neutrons. But what happens when those neutrons get pulled apart by a black hole? What if they don't just get swallowed? What if they get spun into an accretion disk, heated to trillions of degrees, and then ejected in a jet moving near the speed of light? That's not science fiction, that's astrophysics at its most real. And it could explain some of the most powerful gamma-ray bursts we've ever seen. These are events that shine brighter than all the stars in the galaxy combined, for a few brief seconds. Some of them happen so far away that the light takes billions of years to reach us. So when we see one today, we're watching the aftermath of a neutron star's death in the early universe. A death caused, maybe, by a wandering black hole no one saw coming. But we don't just see the light. We now feel the gravitational waves. And this is where it gets even more amazing. In 2015, we detected gravitational waves from two merging black holes for the first time. That discovery changed everything. Since then, we've picked up dozens more, including mergers between neutron stars and black holes. These signals are ripples in spacetime, passing through Earth, stretching and squeezing space itself. They let us hear the universe in a completely new way. And here's what's wild: some of these signals don't match anything we expected. Some of them seem to involve objects in the mass gap, too heavy to be a neutron star, too light to be a regular black hole. Could these be rogue black holes merging with massive neutron stars? Could they be the long-theorized, primordial black holes, ancient objects from the Big Bang itself? We don't know. Not yet. But we're listening. The future of astrophysics might depend on finding more of these strange mergers. And not just detecting them, but understanding them. How often do they happen? What kind of black holes are involved? How do the neutron stars respond? Do they get torn apart first, or swallowed whole? Do they produce jets and light, or just gravitational waves? Every new detection helps us answer those questions, and raises 100 more. The crazy part is, we're still at the beginning. We've only had a few years of data. And already, the universe is whispering secrets we never thought we'd hear. And here's one more thing to blow your mind. When a neutron star merges with a black hole, the result could be more than just a bigger black hole. It could also be a kilogram of pure gold. Or platinum. Or uranium. Because the neutron-rich matter in those stars can undergo rapid neutron capture, a process called the R process, which creates some of the heaviest elements in the universe. That means the gold in your jewelry, the uranium in nuclear fuel, the rare metals in your phone, they might have been forged in one of these cataclysmic events. The collision of a neutron star and a black hole, somewhere out there, billions of years ago, could be responsible for the materials we use every day. Think about that: atoms ripped from the heart of a dying star, scattered into space, drifting for eons, and eventually becoming part of Earth. Part of us. We are literally made of star stuff, and some of that stuff came from the wildest collisions in the cosmos. Years to reach us. But by the time it does, we're witnessing the final scream of a neutron star being torn apart by a rogue black hole. That flash of gamma rays? It's not just radiation, it's a signal that a monster has just fed. And what's left behind? A bigger black hole. One that's now a little more massive, a little more powerful, and still invisible. The event might be over in seconds, but the ripple it sends through space-time, the gravitational wave, can travel forever, undistorted, unweakened. We can catch that ripple with detectors like LIGO and Virgo, and from that one ripple, we can reconstruct the moment a neutron star was eaten alive. But the question we're just beginning to ask is this: what if we're only seeing the easy ones? What if most rogue black hole and neutron star mergers are so clean, so quiet, that we don't notice them at all? If the neutron star gets swallowed whole before it can even disrupt, there's no flash. No disk. No gamma ray burst. Just a gravitational wave, a low-frequency whisper lost in the noise of space-time. That means we might be missing most of these events. Think about that. The cosmos could be littered with merger remnants, silent black holes that have already devoured neutron stars, and we wouldn't even know. They don't light up. They don't roar. They just exist, bigger than they used to be. Some researchers believe that these kinds of mergers might be responsible for seeding larger black holes in dense environments like globular clusters. Over time, one rogue black hole could drift into a cluster of old stars, capture one or two neutron stars, merge with them, and gradually become the heart of that system. It's a slow process, cosmic evolution on billion-year timeframes, but it's plausible. And if that's true, then rogue black holes aren't just random wanderers. They're creators of new systems. Architects of strange cosmic neighborhoods where the rules are different. And still, we ask, where did these rogue black holes come from in the first place? Some are born from stars, supernova remnants flung into space by asymmetric explosions. Others might be primordial, formed in the first seconds after the Big Bang, before stars even existed. If primordial black holes are real, and if even a fraction of them survived until today, then the universe might be teeming with ancient rogues older than any star. These wouldn't just be remnants of stellar death, they'd be fossils of creation itself, relics from a time when physics was different. And if one of those merged with a neutron star? The event might carry signatures of physics we haven't even discovered yet. If primordial black holes are real, and if even a fraction of them survive the violent, chaotic expansion of the early universe, then they could still be out there. Millions or even billions of them, drifting through space completely undetected. These wouldn't be the corpses of stars. They'd be something else entirely. Black holes that never had a parent star to begin with. They might be tiny, or they might have grown over time by consuming dark matter, gas, or even entire stars in the early galactic core. But what makes them even more interesting is how they might occasionally interact with neutron stars, especially in the densely packed environments of early galaxies or stellar clusters. Now imagine this: somewhere, out there in the deep galactic halo, a primordial black hole that formed a trillionth of a second after the Big Bang is on a slow, curving path through a cloud of gas and stars. It's invisible. It has no glow, no pulse, no heat signature. But then it passes near a neutron star, one that's maybe been orbiting the galaxy for billions of years, long after the supernova that formed it. The black hole's immense gravitational field begins to tug at the neutron star, altering its motion in the subtlest of ways. Maybe it takes 1,000,000 years before the two finally meet. But when they do, the result is a cosmic drama we can't yet fully observe. First comes the tidal interaction. The neutron star begins to distort, its dense crust flexing under the stress. This isn't like a rubber ball stretching. This is nuclear matter, denser than anything else in the universe besides a black hole, being deformed. Some theories suggest that during this phase, the neutron star might emit gravitational waves long before the final merger, acting almost like a warning bell. But these signals would be faint, low frequency, hard to detect. Our current instruments may not be sensitive enough to pick them up. As the merger gets closer, the gravitational pull from the black hole intensifies. The neutron star can no longer hold its shape. Its outer layers begin to strip away, forming a tight spiral around the black hole. This accretion process is short, violent, and releases unimaginable amounts of energy. Neutrinos flood space. Magnetic fields twist violently. And then comes the final moment, the collapse. Either the neutron star is completely torn apart and swallowed in pieces, or it's consumed in one horrifying gulp. The difference between these outcomes depends on a tiny balance of masses and spin. If the black hole is too massive, it eats the neutron star whole with almost no radiation. If the neutron star is massive or spinning fast enough, it might resist long enough to generate a massive, brief explosion, a gamma ray burst bright enough to be seen across the universe. And here's the truly bizarre part: we've already detected several short gamma ray bursts, and while we often attribute them to neutron star mergers, there's mounting evidence that some of them might be from neutron stars colliding with black holes. In fact, the LIGO and Virgo collaborations have announced candidate events that fit this exact description. In 2020, for example, gravitational waves were detected from an event called GW200105. The signal was brief, consistent with a black hole merging with a neutron star. No electromagnetic radiation was observed, suggesting that the neutron star may have been swallowed whole. Just like that, one of the most extreme cosmic events we can imagine, and we didn't see a thing. Only the silent ripple of warped spacetime gave it away. But there's another layer to this. Rogue black holes may be responsible for disrupting the lives of binary neutron star systems before they ever merge with each other. In dense star-forming regions, especially in the early universe, there may have been times when a rogue black hole passed near a neutron star binary and perturbed its orbit just enough to send it on a collision course. Think about the chain of events that would set off. One black hole, drifting through space for billions of years, just happens to pass close enough to a neutron star pair to nudge their orbits. Maybe they wouldn't have merged for another 10 billion years, but now, they spiral inward faster. Faster and spiral means a sooner collision. So, in this way, rogue black holes might act as hidden catalysts, accelerating the timeline of cataclysmic events all across the cosmos. And that might not be a rare thing. If our galaxy contains millions of rogue black holes, which some simulations suggest, then it's entirely possible that they're regularly influencing the evolution of star systems. And yet, we have almost no direct evidence of their existence. We know they must be out there. But we've barely scratched the surface of actually detecting them. Some estimates say there could be as many as 100 million stellar mass black holes drifting silently through the Milky Way alone. If even a small percentage of them are rogue, untethered to any star, then we're talking about a hidden population of invisible wanderers, shaping the fate of stars, neutron stars, and maybe even us. Their influence might extend beyond just binary disruption. Some theories suggest that rogue black holes could be responsible for the high-velocity stars we see being flung across the galaxy. If a rogue black hole passes close to a binary system, it can eject one of the stars while capturing or consuming the other. These interactions could explain the origin of hypervelocity stars, stars moving so fast that they can escape the gravitational pull of the Milky Way. That's the kind of indirect evidence that hints at their presence. We see the effect, even if we can't see the cause. And this leads us to one of the biggest mysteries in astrophysics today. How often do these black hole neutron star mergers really happen? And what do they mean for our understanding of heavy elements in the universe? When neutron stars merge with each other, they release material rich in neutrons, perfect for forming heavy elements like gold, platinum, and uranium. But what about neutron star black hole mergers? If the neutron star is swallowed whole, there's no ejection. No elements get released. But if some material is stripped off before the final plunge, we might still get that cosmic alchemy, just in a smaller dose. So the frequency and dynamics of these mergers directly affect how much of the universe's heavy element budget gets produced. That's not just abstract theory. That's the origin of matter. The stuff in your ring, your phone, your bones, might trace back to a single neutron star shredded by a rogue black hole. Are faint, so faint that most of our detectors today wouldn't pick them up unless the event was very close. That means the universe could be filled with whispers of these cosmic warnings, and we'd never know. Only when the final moments arrive, the last seconds before the neutron star plunges into the black hole, do things truly explode into detectability. At that point, the gravitational wave spikes, and depending on the masses involved, a flash of high-energy radiation might follow. But here's the problem. If the black hole is too massive compared to the neutron star, it doesn't get ripped apart. It doesn't flare. It just vanishes. And this gets even crazier when you consider something else. Some of these black holes, especially rogue ones, could have spin. They could be rotating at incredible speeds, twisting space-time itself like a corkscrew. If a fast-spinning black hole merges with a neutron star, the outcome becomes even harder to predict. In certain models, the spin could delay the merger just enough for the neutron star to shed mass and form an accretion disk. That could lead to a short gamma-ray burst. But in others, the spin causes the entire system to collapse into a black hole instantly, with almost no observable aftermath. That makes the job of astronomers infinitely harder because now you don't just need to be in the right place at the right time, you need luck. The right mass, the right spin, the right viewing angle. Still, if we're lucky enough to catch one of these rare events, we can learn so much. When a neutron star is disrupted, it can spew out heavy elements, gold, platinum, uranium, into space. This is one of the leading theories for how the universe got many of its heavy elements in the first place. That's right, your jewelry, your electronics, even some parts of your own body might contain atoms that were forged in the death spiral of a neutron star merging with a black hole. It's not just poetic, it's true. And if rogue black holes are responsible for more of these mergers than we realize, then they're not just cosmic threats. Sculptors of the periodic table. There's also a fascinating mystery surrounding the speeds and trajectories of rogue black holes. Some of them might be moving at hundreds of kilometers per second, kicked out of their birthplaces by violent gravitational slingshots. Others might be drifting lazily, following ancient galactic orbits. But here's the eerie part. Some rogue black holes might actually pass through stellar systems. through solar systems. Even ours. Now, to be clear, the chances of a black hole passing anywhere near Earth are incredibly low. But not zero. In fact, simulations show that over billions of years, rogue black holes could crisscross entire galaxies multiple times, and every so often, one might pass within a few light years of a star like the Sun. If that happened, we might see strange things, outer planets shifting slightly in their orbits, comets being pulled off course, even distortions in the path of light from background stars. But if the black hole didn't come close enough to interact with anything directly, we might never know. It would just drift past in silence, unseen, undetected. Think about that for a moment. There could be a black hole moving through our galactic neighborhood right now, and we wouldn't have a clue. It wouldn't be dangerous unless it got very close, but the fact that we could miss something so massive is humbling. It reminds us just how blind we still are in the face of the universe's vastness. And then there's the question of neutron star populations. How many are there really? We can detect pulsars, spinning neutron stars that beam radio waves at us like cosmic lighthouses, but not all neutron stars are pulsars. Some go quiet. Others are hidden by gas and dust. That means there could be millions of neutron stars in our galaxy alone that we've never seen. And any one of them could be a future meal for a rogue black hole. So when we try to model how often these mergers happen, we're basically guessing with partial information. It's like trying to predict earthquakes without knowing where most of the fault lines are. And yet, scientists are getting better. The more gravitational wave events we record, the more we can constrain the models. And eventually, we'll build a clearer picture of how these cosmic predators hunt. But let's not forget one of the strangest possibilities of all. What if rogue black holes don't just merge with neutron stars? What if they hide inside them? This might sound impossible, but hear this out. There are theories, admittedly, very speculative, that suggest under the right conditions, a small black hole could embed itself within a neutron star. Over time, it would slowly consume the dense matter around it, growing steadily until it destabilizes the entire star. The result? A sudden collapse. A neutron star that seems stable for millions of years suddenly turns into a black hole with no warning. If this is real, it could explain certain fast radio bursts, those mysterious, ultra-brief flashes of radio energy we've detected from across the universe. We don't know what causes most of them. But maybe, just maybe, it's the final gasp of a neutron star that's been quietly eaten from the inside. These are the kinds of ideas that keep astrophysicists awake at night. Not because they're terrifying, though they are, but because they open up whole new ways of thinking about how the universe works. The merger of a rogue black hole and a neutron star isn't just a violent event. It's a lab. A natural experiment where gravity, nuclear physics, and space-time all collide. By studying these mergers, we can probe the behavior of matter at densities we can't replicate on Earth. We can test general relativity in its most extreme form. We can even start to ask deeper questions about the nature of black holes themselves. Because the truth is, we still don't really understand black holes. We can describe them mathematically. We can predict their behavior with incredible precision. But we don't understand them in the way we understand other objects. A black hole isn't just a thing, it's a region of space where the rules break down. Where time slows to a crawl. Where the known laws of physics stop working. And when you throw a neutron star into that mix, a ball of pure nuclear matter, held up only by quantum pressure, you're creating a situation so extreme that it stretches every theory we have. Sometimes, it even breaks them. By the sheer violence of past mergers or gravitational interactions in dense star clusters. These black holes could have been part of binary systems that were torn apart. Imagine two massive stars orbiting each other, one goes supernova, forms a black hole, and the resulting explosion slingshots the black hole into space at insane speeds. Or perhaps two black holes merged, and the uneven gravitational waves from that merger gave the new black hole a recoil kick, launching it like a cosmic cannonball out of its home galaxy. We've even detected candidates for these runaway black holes, moving through space with no visible companions, no accretion disk, no surrounding gas, just gravitational ghosts plowing through the dark. Now picture what happens when one of these fast-moving rogues crosses paths with a neutron star. Unlike binary systems that evolved together over millions of years, this would be a sudden, brutal encounter. A hit-and-run on a cosmic scale. The black hole might barely interact with the neutron star, tugging at it gravitationally but not capturing it. Or it might punch right through it, depending on speed and angle, triggering tidal disruption or even a merger if the conditions are just right. These chance meetings would be extremely rare, but not impossible, and when they happen, they'd create signatures that look nothing like the neat, spiraling waveforms of typical binary mergers. They'd be messy, irregular, almost chaotic. And if we don't know what to look for, we might be missing them entirely. This leads to another wild possibility. Black holes, especially rogue ones, might be responsible for some of the unexplained fast radio bursts, FRBs, we've been detecting. These millisecond-long blasts of radio waves come from random parts of the sky and often repeat with no clear pattern. Some scientists have speculated that they could be caused by neutron stars in high-energy environments, or magnet arcs going through magnetic star quakes. But what if, in at least a few cases, what we're actually seeing is the brief, intense electromagnetic shockwave of a neutron star being grazed, squeezed, or ripped apart by a passing rogue black hole? It would be sudden, violent, and hard to detect except through radio telescopes, exactly like the FRBs we keep picking up. It's still theoretical, but it opens a door to explaining some of the strangest phenomena we observe. And let's not forget about the role of dark matter. This is where things get even more mysterious. Some theories suggest that black holes, especially the smaller ones that don't form from stars, could be made of or cloaked by dark matter. If a neutron star merged with one of these dark matter-dominated black holes, the result might look very different. The gravitational wave signature could be weaker. The electromagnetic radiation might be almost non-existent. It might be a completely invisible event. In that case, we wouldn't even know it happened unless it occurred close enough for LIGO or Virgo or other gravitational wave detectors to pick up the subtle ripple in space-time. And if dark matter interacts differently with neutron stars than regular matter does, we might be looking at an entirely new type of merger event, something that doesn't match any known waveform, doesn't produce light, and doesn't leave behind any observable debris. Just a slight hiccup in the fabric of spacetime, barely noticed unless we're paying very, very close attention. Go even deeper. Think about what happens right before the moment of impact, before the neutron star and rogue black hole collide. There's a fleeting phase of extreme tidal distortion. The black hole's gravity stretches the neutron star like taffy, warping its dense matter into an elongated spiral. If the neutron star isn't swallowed whole immediately, it begins shedding its outer layers, spraying exotic particles and radiation into space. And those particles aren't your average space dust. We're talking about matter that's been crushed to densities greater than an atomic nucleus, held together by neutron degeneracy pressure, something you don't find anywhere else in the universe. It's so dense that a teaspoon of it would weigh more than 1 billion tons. So when this stuff gets ejected, even in tiny amounts, it can create radioactive decay signatures that glow for weeks. This glow, called a kilonova, has been seen in some neutron star mergers. But what if rogue black holes are triggering kilonovae without us realizing it? This also ties into one of the biggest puzzles in astrophysics right now, the origin of the heaviest elements. We used to think supernovae made all of them, but that's not adding up. The numbers don't match. Now it looks like most of the gold, platinum, and uranium in the universe might actually come from neutron star mergers. But here's the catch. Binary neutron star systems that eventually merge are rare. Not rare like winning a scratch ticket. Rare like winning the lottery 3 times in a row. So if we're seeing more heavy elements than our current models predict, something else must be helping to make them. Rogue black hole, neutron star collisions could be that missing piece of the puzzle. They may be more frequent than we realize, just harder to detect because they don't always emit the same kinds of signals. And then there's the ultimate mystery. What happens inside a neutron star right before it gets torn apart? This is one of the most extreme environments in the universe. The pressure and density inside a neutron star are so intense that atoms themselves cease to exist in their normal form. Some theories suggest the core could be made of quark matter, a soup of up and down quarks freed from protons and neutrons. Others think strange matter could form, an even more exotic state where strange quarks come into play. And when the black hole starts pulling the neutron star apart, it might expose this core to the universe for the first time. If we could detect the particles and radiation that come from this moment, we might finally understand what matter looks like under the most extreme pressure possible. Something we can't recreate in any lab on Earth. But again, most of this relies on us being lucky. Rogue black holes are fast, quiet, and cold. Neutron stars don't live in crowded places. They're often flung far from their birthplaces after their supernova. So these two cosmic loners have to find each other in the vast emptiness of space. It's like two needles trying to collide in a haystack the size of a galaxy. But when it happens, the universe changes. Space bends, time stretches, light flickers, and the building blocks of planets, people, and everything we know might be forged in that fleeting moment. And that's the beauty of it, the idea that even the most violent, chaotic events in the cosmos might also be its most creative. Black hole merges with the neutron star, all of that dense, exotic matter gets violently compressed, twisted, and possibly converted into something we've never seen before. It's not just destruction, it might be transformation. The process could momentarily create conditions similar to the birth of the universe itself, with temperatures and densities so extreme that new types of particles or even unknown states of matter might briefly appear and vanish before we can detect them. This is where the frontier of astrophysics and particle physics collide, literally. Scientists have proposed that in the split second before the neutron star is completely devoured, a burst of neutrinos could be released. Tiny, nearly massless particles that barely interact with anything, but carry away huge amounts of energy. These neutrino bursts could be a smoking gun for identifying such collisions, especially when paired with gravitational wave data. But detecting them is like trying to catch a single grain of sand in a hurricane. We need detectors buried deep underground, shielded from all other particles, just to have a chance of noticing a few of them. The real kicker? Some of these collisions might not produce light at all. They could be what scientists call dark mergers, where the only detectable signal is a ripple in space-time itself. No gamma rays, no radio waves, no visible light, just gravitational waves echoing across the cosmos like the deep bass notes of a song we're only beginning to hear. That's why instruments like LIGO, Virgo, and CAGRA are so important. These are gravitational wave observatories sensitive enough to pick up distortions in spacetime caused by massive objects colliding light-years away. When they detect something unusual, like a merger with an unexpected mass ratio, or a waveform that doesn't match known black hole or neutron star signatures, it might be a rogue black hole encountering a neutron star. These anomalies are gold mines for discovery, and researchers spend months combing through the data to figure out what really happened. And it gets even stranger. Some theories suggest that in very specific scenarios, the merger of a black hole and a neutron star could leave behind an object that defies classification. Not a neutron star. Not a black hole. But something in between, an intermediate object that temporarily resists collapse, may be held together by ultra-dense matter or quantum effects. This hybrid remnant could last for milliseconds or even seconds, emitting gravitational waves and bursts of radiation unlike anything we've ever recorded. If we ever manage to catch one of these in the act, it could completely change our understanding of gravity, quantum mechanics, and the ultimate fate of matter. Of high-energy radiation before finally collapsing into a black hole. During that brief window of time, this object could reveal secrets about matter under the most extreme pressure known to science, conditions that can't be replicated in any lab on Earth. These hybrid remnants are theoretical, but if we could confirm their existence, it would rewrite our understanding of the nuclear forces that govern matter, and might even challenge our models of general relativity and quantum physics. Now imagine this scenario playing out not in isolation, but somewhere in the early universe. Back when galaxies were still forming, when stars were closer together, when the rate of stellar death was much higher. Rogue black holes could have been far more common back then, leftovers from violent gravitational collapses, ejected from their birth galaxies by powerful gravitational interactions or mergers. With neutron stars also being formed in large numbers due to the rapid birth and death of massive stars, the early cosmos might have been a collision zone filled with these strange encounters. And here's the twist. These early collisions could have seeded galaxies with heavy elements, changed the distribution of matter, and shaped the large-scale structure of the universe. We might be walking around today with atoms in our bodies that were forged in the chaos of one of these ancient rogue black hole, neutron star mergers. But there's another layer to this mystery: the velocity of rogue black holes. When black holes are born from supernova explosions, they often receive a kick, launching them through space at incredible speeds. Some can move at over 1,000,000 kilometers per hour, fast enough to escape their host galaxy entirely. These high-velocity black holes are the ultimate cosmic drifters, wandering through interstellar space, invisible unless they happen to interact with something. And that something could be a neutron star. If their paths intersect, even a near miss could have catastrophic consequences. The black hole's immense gravity would start pulling material from the neutron star, forming a disk of superheated matter around it, what we call an accretion disk. This disk shines brightly in X-rays and gamma rays, making it temporarily visible to telescopes on Earth. But once the neutron star is consumed, the light vanishes again, and the black hole continues on its lonely journey, leaving behind nothing but gravitational echoes. And this brings us to a haunting possibility: that many of these mergers are happening undetected in the vast voids between galaxies. These are regions of space so empty that even light takes millions of years to cross them. If a rogue black hole collides with a neutron star in one of these cosmic deserts, the resulting explosion or gravitational wave event might never reach us, or reach us so faintly that our instruments can't pick it up. That means we could be missing an entire class of astrophysical events that are shaping the universe from the shadows. Events that could explain dark matter behavior, the distribution of heavy elements, or even anomalies in the cosmic microwave background. And we wouldn't even know it. Now, let's go even deeper into the mechanics of the collision itself. The process doesn't happen in an instant, it's more like a death spiral. As the black hole and neutron star draw closer under each other's gravitational pull, they emit gravitational waves, ripples in the fabric of spacetime. These waves carry away energy, causing the objects to spiral inward faster and faster. In the final moments, the neutron star may become tidally locked to the black hole, its matter stretching and bulging like a drop of water about to be sucked into a drain. And if the mass ratio is just right, the neutron star will be torn apart before it crosses the event horizon. This is critical, because it determines whether we get an electromagnetic signal, something we can detect with telescopes, or just a clean gravitational wave signal. If the black hole is too massive compared to the neutron star, it swallows the neutron star whole, in one gulp, leaving almost no debris. That's harder for us to detect because it doesn't produce much light. But if the masses are closer, especially if the black hole is spinning fast, the neutron star can be shredded outside the event horizon, releasing a torrent of radiation, gamma rays, X-rays, neutrinos, and visible light. This is where kilonovae come from, those brilliant, short-lived bursts of light that fade within days. They're incredibly rare, and even harder to spot, but they offer a clear fingerprint of neutron-rich material being flung into space and undergoing radioactive decay. And it's this process, our process nucleosynthesis, that creates the heaviest elements on the periodic table. So when you hold a piece of gold or platinum in your hand, you're literally touching the remains of a cosmic disaster. That material was forged in the heart of a dead star and torn from it during a collision with something even more extreme, a black hole with no home, no orbit, and no warning. And the eerie part? That black hole could still be out there, moving silently through space, invisible until it finds its next victim. There's also an unanswered question that keeps astronomers up at night. How often do these rogue black hole, neutron star mergers actually happen? Estimates vary wildly because they depend on so many unknowns. How often black holes are ejected from galaxies, how many neutron stars are drifting in the same regions, how far out into space our instruments can detect gravitational waves. Some estimates suggest they might happen as frequently as once a year in the observable universe. Others say it could be once every 1,000 years. The truth is, we don't know. But what we do know is that as our technology improves, especially with next-generation gravitational wave detectors like the Einstein telescope and Cosmic Explorer, we'll start hearing more of these faint signals from deep space. And each one could be a clue to unraveling a mystery that has existed since the dawn of time. Mergers might never produce light we can see, never leave behind glowing remnants, and never emit the kind of electromagnetic signatures our telescopes are tuned to detect. Instead, they might be silently shaping the cosmos in ways we can't fully comprehend, disrupting star systems, altering galactic dynamics, or generating gravitational waves that travel for billions of years before they ever reach Earth. Think about that. Right now, a signal from a rogue black hole merging with a neutron star could be traveling across space toward us, a message from a cosmic event that happened long before Earth even existed. And when that signal finally arrives, if we're lucky enough to catch it, it will last just seconds, seconds that contain data from an explosion of unimaginable violence and complexity. Even more intriguing is how these mergers might interact with dark matter, the mysterious substance that makes up most of the mass in the universe but doesn't emit or absorb light. Some scientists believe that dark matter might clump around massive objects like black holes. So when a rogue black hole passes through a region rich in dark matter, or when it merges with a neutron star surrounded by dark matter, it could cause unexpected gravitational effects. These interactions could alter the merger's signature, change the behavior of the gravitational waves it emits, or even produce exotic forms of energy that we've never seen before. In some speculative theories, such mergers could trigger the collapse of dark matter into even denser objects we don't even have names for yet. If that's true, rogue black holes might not just be colliding with neutron stars, they might also be awakening something deeper and darker in the cosmic fabric. And then there's the role these mergers might play in cosmic recycling. When two massive objects collide, the explosion doesn't just destroy, it creates. Elements like gold, platinum, and uranium are believed to be born in the aftermath of neutron star collisions. If a black hole consumes a neutron star too quickly, these elements may be swallowed before they can escape. But if the merger is just right, if the neutron star is torn apart before being fully consumed, it might scatter these heavy elements into space. Over time, those elements mix into clouds of gas and dust, which later form new stars and planets. So in a way, these violent encounters are part of the life cycle of the universe. They help create the building blocks for planets, ecosystems, and even life. And even life itself, when you think about it, could be the direct result of these brutal cosmic collisions. Every atom of gold in your jewelry, every bit of uranium in a nuclear reactor, and possibly even some of the rarest isotopes in your body, could have originated from a rogue black hole ripping apart a neutron star billions of years ago. That's not just poetic, it's astrophysical reality. These collisions are not rare artistic accidents of the universe. They're factories. They're forges. They're the universe's way of taking the raw, lifeless elements of hydrogen and helium and smashing them together until something new is born. We're not just observing this from a safe distance, we're made of it. We are the aftermath of cosmic violence. Now, here's another wild thread to pull on. What if these mergers are hiding in plain sight? Scientists have started to wonder if some of the fast radio bursts, FRBs, we occasionally detect, those mysterious, split-second flashes of radio waves from deep space, might actually be related to rogue black hole, neutron star encounters. FRBs are still mostly a mystery. We've only just begun to classify and trace them. But some theorists have suggested that when a black hole passes close enough to a neutron star, it might trigger violent magnetic activity, especially if the neutron star is a magnetar, a neutron star with an insanely powerful magnetic field. This interaction could create a flash of radio energy visible for only milliseconds across vast cosmic distances. That means the signal we detect today might be the whisper of a black hole brushing past a neutron star millions of light years away. And think about how terrifyingly quiet that is. In most scenarios, a rogue black hole gives no warning. It moves invisibly through the galaxy until it finds a victim, like a neutron star, and then consumes it in a flash. There's no long build-up. No slow spiral. No drawn-out drama like we see with regular binary black hole mergers. It's fast. Brutal. Final. And unless we just happen to be looking at the exact right place at the exact right time with the right kind of detectors, we miss it. It happens without a trace. No light. No noise. Only gravity carries the story, rippling through space like a ghost of violence. We call those gravitational waves, and we've only been able to detect them since 2015. Think about how much we've missed before that. Think about how much we're still missing. Now, not every merger between a rogue black hole and a neutron star ends the same way. The outcome depends on a lot of factors: mass, spin, velocity, angle of collision, and the density of surrounding space. If the neutron star is massive enough and the black hole is relatively small, the neutron star might not even be swallowed right away. It might resist, deform, or even break into fragments that orbit the black hole briefly before falling in. These fragments could emit light, energy, even jets of matter moving at nearly the speed of light. Those jets could collide with surrounding material and create visible explosions, gamma-ray bursts, the most powerful kind of light we know. And if that happens, we might see it. We might catch a burst of light that tells us exactly where a black hole just consumed a star made entirely of neutrons. But there's more. Some theorists are now considering that in the chaos of these collisions, we might briefly form a state of matter known as quark-gluon plasma, the same kind of matter that existed in the first few microseconds after the Big Bang. This plasma is so hot and dense that the fundamental building blocks of protons and neutrons, quarks and gluons, roam freely unbound. If that's true, then every rogue black hole, neutron star collision could briefly open a window into the birth of the universe itself. For a moment, we're not just witnessing stellar death, we're reaching back into time, watching the early conditions that gave rise to everything. Our galaxies. Our solar system. Us. And here's the real kicker: these events could also be responsible for seeding black holes that become supermassive. If a rogue black hole consumes a neutron star and continues to merge with more compact objects over time, growing steadily, it might become the seed for the kind of black holes we find at the center of galaxies, millions or billions of times the mass of our Sun. These aren't just curiosities. They are the engines of galaxies, shaping the rotation, evolution, and structure of entire star systems. That means a single rogue black hole, wandering the void and quietly devouring stars, could grow into a monster that one day anchors an entire galaxy. The ripples from that one event stretch across time and space, influencing the structure of the cosmos itself. So when we talk about rogue black holes merging with neutron stars, we're not just talking about rare accidents. We're talking about a process that might be far more common, far more important, and far more influential than we ever imagined. We're talking about cosmic alchemy. About the creation and destruction of matter on a scale we can barely comprehend. About events that reshape the universe while we sleep, while we go to school, while we look up at the stars with no idea what's actually happening out there in the dark. Listen to them for a few short years. Think about that. For the entire history of humanity, these waves were traveling through Earth unnoticed, passing through our bodies, our cities, our oceans, without a single human being ever knowing they existed. It wasn't until 2015 that we finally caught one. Just one. And now, with detectors like LIGO and Virgo and Cagra, we're starting to hear the whispers of the universe. Every detection is a message, a cosmic telegram from something far away and unimaginably powerful. And among those whispers, we're starting to notice patterns, events that don't quite fit the usual mold. Signals that might not be from binary black holes or binary neutron stars, but something stranger. Something rarer. Possibly the signature of a rogue black hole colliding with a neutron star. These aren't just small bumps in data, they're anomalies that demand explanation. When these mergers happen, the physics is extreme. We're talking about gravity strong enough to bend light into a full circle. matter so dense that a teaspoon of it would weigh billions of tons. Magnetic fields that could erase all the data on Earth's hard drives from thousands of light years away. Temperatures hotter than the cores of stars. And pressures so high that atoms themselves are crushed into a soup of quarks and gluons. We don't know what happens at that level. Our equations break. General relativity starts to buckle. Quantum mechanics throws up its hands. And in that chaos, in that cosmic pressure cooker, something new might form, something we've never seen. Some physicists speculate that inside these violent mergers, strange matter might emerge, a form of matter more stable than normal atomic nuclei. If it does, and it escapes, it could theoretically turn other normal matter into strange matter on contact. It sounds like science fiction, but it's based on real theoretical physics. The idea that one rogue merger could seed the galaxy with a whole new kind of matter is both terrifying and thrilling. But even if strange matter never escapes, the energy involved in these collisions is enough to warp space-time itself. The gravitational waves they produce stretch and squeeze the fabric of the universe as they pass. If you were close enough to the collision, say, within a few light years, you wouldn't just feel the blast of radiation. You'd feel space itself move. Your sense of direction would twist. Distances would contract and expand. And time? Time would stutter. For just a moment, the regular rhythm of the universe would skip a beat. If a rogue black hole merges with a neutron star somewhere in our galaxy, we might see the aftershock in gravitational waves, gamma ray bursts, and even changes in pulsar timing. Some scientists are already using pulsars as cosmic clocks, looking for tiny irregularities in their signals that might indicate a gravitational wave passed between us and them. That's how delicate our instruments are becoming. We're learning to read the universe by noticing what doesn't happen, what's missing, what's just a little off. In that silence, in those gaps, lies the story of cosmic collisions happening far beyond our view. And what about the aftermath? Let's say a rogue black hole tears a neutron star apart. What's left? If the neutron star is completely consumed, we might be left with a slightly larger black hole, darker, denser, and moving even faster through space. But if the neutron star is only partially eaten, it could eject enormous jets of matter into space. Those jets might travel at near light speed, heating up surrounding gas, triggering shockwaves, and even igniting star formation in nearby clouds. In this way, a single merger could act like a galactic defibrillator, jump-starting new stars, shaping galaxies, and redistributing matter across vast distances. And the radiation from that explosion might bathe planets thousands of light years away in high-energy particles, altering their atmospheres and possibly triggering evolutionary changes in any life forms unlucky, or lucky, enough to be nearby. That's not just theory. There's evidence on Earth, buried deep in our oceans and rocks, that we may have been hit by radiation from distant supernovae or cosmic events in the past. If that's true, then rogue black hole mergers might have already touched our planet, maybe even influenced our biology. And yet, for all this, we've never seen one happen. Not clearly. Not directly. That's the great cosmic irony. These events are so powerful they shape the universe, but so fleeting and subtle that we still struggle to catch them. We're like people on a dark beach listening for thunder from a distant storm, trying to figure out what lightning looks like based only on the echoes. We're getting better. Our instruments are improving. Our theories are evolving. But space doesn't give up its secrets easily. Every answer leads to more questions. What kinds of black holes go rogue? Are they born that way, or do they get kicked out of their systems? Are rogue mergers more common in the early universe? Do they play a role in shaping the distribution of galaxies? Could they explain some of the most energetic events we've seen but never fully understood? And most chilling of all, could one be on its way toward us right now? Would momentarily lose all meaning. You wouldn't just be thrown around like in an earthquake. Space itself would ripple underneath you. And you wouldn't see the wave pass, but every atom in your body would know it was there. These distortions are so subtle by the time they reach Earth that we need equipment that can detect changes thousands of times smaller than a proton to even register them. That's what LIGO does. It's that precise. But imagine being close enough to feel those distortions at their full strength. It's not just unimaginable, it's unknowable. Our brains aren't wired to even conceptualize that kind of event. It's like trying to understand what it's like to be inside a black hole. There's no reference point in the human experience. Now let's talk about how rare and important these events are in the evolution of galaxies. When a rogue black hole collides with a neutron star, it doesn't just end there. The aftermath is intense. It throws off radiation, it alters local magnetic fields, it can even redirect or slow down star formation in the region. Think of a galaxy as a living thing. These collisions are like sudden shocks to the system, seismic events that ripple through the structure. They send out gamma ray bursts, some of the most powerful explosions in the universe. These gamma ray bursts, or GRBs, can sterilize entire regions of a galaxy, potentially wiping out life if they're pointed in our direction. Scientists believe that Earth may have been hit by 1 million years ago. One single burst, coming from a merger thousands of light years away, could cause a mass extinction. That's the kind of power we're talking about. It's not just a dramatic explosion. It's a weaponized force of nature on a cosmic scale. But on the flip side, these mergers also give us elements we need to live. Every heavy element beyond iron is formed through a process called rapid neutron capture, or our process nucleosynthesis. That process requires extreme environments, like those found in neutron star mergers. That means that every bit of platinum, gold, lead, uranium, those were forged in the fire of a neutron star being torn apart by a black hole. When we detect the light from one of these events, we're actually seeing the creation of these elements in real time. The light is tinted by them. That's how scientists knew they had seen gold and platinum being created in the 2017 neutron star merger, by analyzing the light and identifying the chemical fingerprints. And when a rogue black hole collides with a neutron star, it can produce even more exotic outputs. The ejecta from these events, the material thrown off, can move at a significant fraction of the speed of light. It escapes into the galaxy, mixes with interstellar gas, and eventually becomes part of new stars, planets, and life. You and I are literally made of the debris of these violent, beautiful collisions. And that brings us to one of the strangest questions of all. Could rogue black hole, neutron star collisions be responsible for the origins of life itself? It sounds ridiculous, right? But think about it. Without those elements, DNA can't form. Cells can't function. Planets can't differentiate. Plate tectonics, which help regulate the climate and maintain life, wouldn't exist. Without uranium, there's no natural geothermal heating. Without molybdenum or cobalt or nickel, enzymes can't do their job. We think of supernovas as the main source of heavy elements, but they can't account for all of them. It's these mergers, rare, sudden, violent, that supply the rest. It's possible, then, that life on Earth exists because billions of years ago, a black hole ripped a neutron star apart in some distant part of the galaxy, flinging its guts across space, some of which found their way into the molecular clouds that formed our sun and our planet. That's not just poetic, it's grounded in real, observable astrophysics. And the universe is probably full of these events. Rogue black holes are more common than we thought. Neutron stars, though hard to detect, are all over the place. Put those two facts together, and you get the possibility that these collisions are happening all the time. We're just not seeing them. They could be cloaked in darkness, in parts of the galaxy we don't watch, in wavelengths we haven't developed detectors for yet. Some might even be happening behind the veil of black hole event horizons, totally hidden from our view. But their fingerprints are everywhere, in the elements, in the gravitational waves, in the fast radio bursts, and maybe even in us. Being created, not metaphorically, but literally, gold forming out of the chaos of a neutron star being shredded by a black hole. It's like cosmic alchemy, but with real physics. And when that material gets blasted into space, it doesn't just vanish. Over millions of years, it drifts, spreads, and gets woven into new stars, planets, and eventually, life. The gold in your jewelry, the uranium powering nuclear reactors, even some of the iodine in your body, All of it could trace its origins to a moment where a rogue black hole slammed into a neutron star in some forgotten corner of the galaxy. That's not just cool trivia. That's cosmic history written into our bones. These collisions are rare, but when they happen, they write the next chapter of the universe. Without them, the periodic table would look very different, and so would we. Now, the rogue nature of these black holes makes it even more fascinating. Most black holes we know about are part of binary systems. They orbit something, or something orbits them. But rogue black holes are loners. They've been ejected from their original systems, often by gravitational interactions or even other mergers. When two black holes merge, the final object can get a kick, a powerful recoil from asymmetric gravitational wave emission that shoots it out of its galaxy or across interstellar space. Imagine a black hole flying through the galaxy at thousands of kilometers per second, invisible, silent, deadly. And eventually, one of these cosmic assassins comes close enough to a neutron star to pull it in. It's not some elegant dance over millions of years like with traditional binary systems. It's fast, violent, and unpredictable. One moment the neutron star is drifting through space. The next, it's spiraling into oblivion, twisted and torn by tidal forces so strong they could rip the crust of a planet into dust. These rogue collisions could happen in places we don't expect. Maybe even in regions of space that we consider quiet, far from star-forming regions, in the galactic halo, or deep in intergalactic space. And when they happen, they could produce signals different from anything we've cataloged so far. The gravitational wave signature from a rogue black hole, neutron-star merger could be off-axis, or lopsided, or exhibit weird frequency modulations that hint at an unusual mass ratio or spin configuration. Scientists are just starting to recognize these kinds of patterns. In fact, a few detections have already puzzled researchers. Objects that are too heavy to be neutron stars but too light to be black holes, or mergers that show unexpected dynamics. It's possible that we've already seen a few rogue black hole events and just didn't know it yet. Now let's dive even deeper into what happens during the actual collision. As the neutron star spirals inward, it gets stretched by tidal forces. Depending on the mass of the black hole, the neutron star may get disrupted before it crosses the event horizon. This is called tidal disruption. If the black hole is relatively small and the neutron star relatively large, the neutron star can be pulled apart outside the event horizon, creating an accretion disk. This disk is a swirling, superheated mess of nuclear matter, spinning at nearly the speed of light. Inside this disk, temperatures soar to billions of degrees. Particles smash together with so much energy that exotic reactions begin to happen. Neutrinos are produced in insane quantities. And magnetic fields go berserk, twisting and snapping like cosmic whips. These magnetic fields can funnel matter into jets, high-speed streams of plasma that burst out of the poles of the black hole, releasing gamma rays across the universe. These gamma ray bursts are so bright, they can outshine entire galaxies for a few seconds. If one of those bursts was aimed at Earth from a few thousand light-years away, it could wreck our atmosphere, destroy satellites, and potentially cause a mass extinction. But even if we're not in the path, the burst is a signpost. It tells us something massive just happened. And by analyzing the light, scientists can reverse engineer the event. The color of the light, the decay curve of the afterglow, the spectral lines, all of it tells a story about what kind of objects collided, what elements were created, and how much mass was ejected. It's like reading the forensic report of a cosmic crime scene. Now here's where it gets even weirder. Sometimes, after a merger like this, a remnant might survive, at least for a little while. Depending on the mass and the equation of state of nuclear matter, which we still don't fully understand, the collision might not instantly create a black hole. Instead, it might create a hypermassive neutron star, a Frankenstein-like object held together by rapid rotation and magnetic pressure. These remnants are unstable, doomed to collapse into a black hole within milliseconds or seconds. But while they exist, they could emit bizarre forms of radiation, including fast radio bursts, short, powerful bursts of radio waves that we've detected from galaxies billions of light-years away. Some astrophysicists think these bursts might be the death screams of hypermassive neutron stars just before they collapse. If that's true, then rogue mergers might be responsible for at least some of the FRBs we're seeing. It's not just a theoretical playground either. We're now living in the age of multi-messenger astronomy, which means we don't just rely on one kind of signal. We watch the universe in light, in gravitational waves, in neutrinos, in cosmic rays. And the more of these messengers we catch from a single event, the more we can learn. Imagine seeing a gamma ray burst, detecting gravitational waves from the same region, catching a flash of visible light in a telescope, and spotting a neutrino spike at the same time. That's not science fiction, it's happening. In 2017, with the famous GW170817 event, we caught gravitational waves, light, and gamma rays from a neutron-star merger. That single event taught us more about the universe than decades of previous research. Now imagine doing the same thing, but with a rogue black hole, neutron-star collision. We're standing on the edge of a new frontier, one where every detection could rewrite textbooks. And we're not just waiting around either. New detectors are coming online. LIGO is getting upgrades. New facilities like the Einstein Telescope and Cosmic Explorer are being designed. They'll be able to detect more distant, fainter, and more exotic events. We'll be able to tell when a rogue black hole starts tugging on a neutron star before the collision even happens. We might even be able to point telescopes at the location before the light arrives, watching in real time as one of the most powerful events in the universe unfolds. This isn't a distant dream, it's within reach. And as our tools get better, our understanding will deepen. We'll stop being passive observers and start becoming real-time witnesses to the most violent, beautiful events in the cosmos. Because unlike binary mergers where we've tracked the orbital dance for ages, these rogue collisions don't follow the same rules. They're chaotic. The black hole may come in at an odd angle, with a velocity far exceeding that of a typical binary companion. That changes everything. It changes the gravitational wave signature. It changes the way the neutron star is torn apart. It even changes whether or not we get a visible light signal at all. Sometimes the neutron star might be swallowed whole, disappearing without a trace, giving us nothing but a short gravitational whisper before silence. Other times, the neutron star could be ripped apart just before the black hole devours it, flinging pieces of itself out into space, lighting up the sky with X-rays, gamma rays, and radio waves. That's what scientists call a kilonova, a blast so bright that it outshines an entire galaxy for a few fleeting moments. And that light carries secrets. It tells us about the makeup of the neutron star, the spin of the black hole, the direction of the collision, and the ingredients that are now being thrown back into the universe. But these rogue collisions are more than just explosions. They're time machines. When we detect the gravitational waves from one, we're hearing echoes from millions, sometimes billions, of years ago. These waves have been traveling across the fabric of space-time since long before humans walked the Earth. And because gravitational waves aren't blocked or scattered like light, they give us a pristine, undistorted snapshot of that ancient event. It's like tuning into a cosmic broadcast from the past. And every time we catch one, we add another puzzle piece to the great story of how the universe builds itself. And the more of these collisions we detect, the more we realize how incomplete our understanding is. For instance, there are models predicting that some rogue black holes might have formed in the early universe, primordial black holes. These aren't made from stars, but from density fluctuations shortly after the Big Bang. If a primordial black hole were to collide with a neutron star today, it might look very different from any merger we've seen. It might not emit any electromagnetic signal at all. Or it might emit something completely unfamiliar, an unexplained burst of radiation or particles we've never seen before. That's why every single event matters. Because every merger is a test of our theories. Every strange signal is a possible window into something new. There's also the possibility that some of these events could produce exotic matter, forms of matter that can't exist under normal conditions. Neutron stars themselves are already extreme. Their cores might contain quark-gluon plasma or other exotic phases of matter that we've never recreated on Earth. When a black hole rips open a neutron star, it could expose these cores for a split second, giving us a glimpse at what the universe looks like at its absolute limits. And if even a fraction of that material escapes the black hole's grip, we might detect it with our most sensitive instruments, signals that defy known physics, particles that shouldn't exist. Some scientists even speculate that such mergers could help explain dark matter or other cosmic mysteries we've yet to understand. And this is where the story really starts to get wild. Because if black holes can go rogue, if they can wander the galaxy, collide with neutron stars unexpectedly, and create signals that don't match anything we've cataloged, then what else are we missing? Could some of the fast radio bursts we've detected be from these collisions? Could some unexplained gamma-ray spikes be the aftershock of a black hole devouring a star it was never supposed to encounter? Could these events be shaping galaxies in ways we've never considered? There's a theory that rogue black holes might be responsible for helping regulate galaxy formation. As they pass through interstellar clouds, they can heat up gas, trigger star formation, or disrupt it entirely. They can seed chaos or carve structure. And over billions of years, their wanderings might have shaped the very arms of spiral galaxies or stirred up galactic halos in ways we don't yet understand. These aren't just lone wanderers, they're hidden sculptors of the cosmos. And maybe, just maybe, they're more common than we think. Is a potential doorway into new physics. That's not an exaggeration, it's exactly how our understanding of the universe grows. Each time a rogue black hole merges with a neutron star, the universe is effectively writing us a message in gravitational code. And with detectors like LIGO, Virgo, and now Kagra and Lisa on the horizon, we're finally starting to learn how to read it. But here's the thing, most of these signals are so faint, so far away, or so strange that they might escape our notice entirely. That's why researchers are building more sensitive detectors, and why artificial intelligence is being trained to sift through petabytes of data looking for patterns that the human brain might miss. We're not just waiting for these events to come to us anymore. We're actively hunting them. Now let's dig into the anatomy of what really happens when a rogue black hole collides with a neutron star. It starts with gravity. At first, the black hole might be moving freely through interstellar space, just minding its own business, if you can say that about an object with infinite density. Then, by sheer cosmic chance, it passes close to a neutron star. And not just any distance close enough for its gravitational field to grab hold of the neutron star's mass. The black hole starts pulling. The neutron star responds. It begins to spiral inward, dragged along a death path, spinning faster and faster, stretching and distorting under the relentless tidal forces. The crust of the neutron star, already the densest matter in the universe outside of a black hole, starts to crack. The magnetic fields, trillions of times stronger than anything we can generate on Earth, begin to twist and snap, releasing bursts of energy. Then the real chaos begins. In the final moments, the neutron star may be torn apart into streams of plasma that whip around the black hole before falling in. These streams heat up to billions of degrees, glowing in gamma rays and X-rays. The collision may also generate a relativistic jet, narrow beams of matter traveling at nearly the speed of light, blasting into space and lighting up the cosmos. If Earth is in the path of that jet, we see it as a short gamma-ray burst, one of the most energetic explosions in the known universe. But if the jet is angled away from us, we may miss the light entirely, and only detect the gravitational waves. And here's a wild thought, some of these collisions might result in something completely new. If the neutron star isn't fully consumed and instead forms a dense disk of matter around the black hole, that disk could become unstable. It could collapse. Or it could stick around for a while, forming what's known as an accretion disk, feeding the black hole for millions of years. This process could even produce a magnetar, a highly magnetized neutron star remnant, or a hybrid object we've never seen before. Some theorists even speculate about the temporary formation of a quark star, an exotic object made entirely of free-floating quarks. No one's observed one yet, but a rogue collision like this might be the birthplace. And here's another layer to it. The population of rogue black holes could be massive. Our galaxy alone might be home to hundreds of millions of them. Most are completely invisible, unless they interact with something. But when they do, when they catch a neutron star, or even a white dwarf or normal star, the event is loud, messy, and full of clues. There could be rogue black holes just a few hundred light years from Earth, drifting silently through the dark, and we wouldn't even know it. The only way we might find them is if they happen to collide with something or lens the light from a background star, creating a telltale signature. Now picture the implications for the origin of elements in the universe. We know that gold, platinum, and other heavy elements aren't created in supernovae alone. It takes neutron-rich environments, like those produced in mergers. If rogue collisions are more common than we think, they could account for a much larger portion of the universe's heavy elements than we've previously estimated. This would completely rewrite our models of galactic chemical evolution. It would change how we understand the formation of planets, moons, and even the biology of life, since so many essential elements, like iodine, thorium, and uranium, come from these explosive events. And we're just scratching the surface. There's still the mystery of what happens inside the event horizon once the neutron star is swallowed. Classical physics says it disappears. Quantum physics suggests information must be preserved. Is it scrambled and smeared across the surface of the black hole? Is it encoded in the gravitational waves? Could rogue collisions help us test the limits of the holographic principle, the idea that the entire universe is a projection from a two-dimensional surface? These aren't just abstract thoughts, they're ideas that can be tested with real data, if we can detect enough of these collisions. Even the path that rogue black holes take before impact matters. If a rogue black hole passed near a star system, it could disrupt planetary orbits, slingshot asteroids, or eject entire stars from the galaxy. We've seen stars moving at absurd speeds, hypervelocity stars, that could be the result of such encounters. These rogue black holes may not just be cosmic cleanup crews, they might be cosmic wrecking balls, reshaping galaxies and solar systems in their wake. And imagine the storytelling potential. Every neutron star, black hole merger is a drama playing out over eons, a celestial tragedy written in the language of gravity and light. One was a massive star that lived fast and died young, collapsing into a neutron star. The other, once part of a binary system, perhaps, was flung into the void after its own cataclysmic collapse. They drift for millions of years, destined never to meet, until chance, gravity, and timing bring them together in one final, spectacular moment. We're left with only the gravitational wave signature to tell the story. That's the risk and the reward of studying rogue mergers. Every event is unique, and every signal is unpredictable. In some cases, astronomers only catch the faint ripple in space-time without any accompanying light, making it incredibly difficult to determine the exact nature of the objects that collided. Was it a black hole and a neutron star? Two black holes? A neutron star and something stranger? That's where things get fascinating, because when something doesn't match our models, we have to face the possibility that it might be something entirely new. One of the most tantalizing ideas in astrophysics is that some of these unexplained mergers might involve exotic objects like quark stars or boson stars, hypothetical forms of matter that exist beyond the standard model of physics. Quark stars, for example, are thought to be even denser than neutron stars, composed entirely of deconfined quarks, the building blocks of neutrons and protons. If a rogue black hole were to collide with one, the gravitational wave signature could be subtly different, hinting at the existence of matter we've never directly observed. And if a boson star were involved, the signature might be even more bizarre. These stars wouldn't be made of normal matter at all, but of fundamental particles called bosons, possibly linked to dark matter. Detecting a merger with one of these objects could crack open the door to understanding the dark sector of the universe, the invisible mass that makes up more than 80% of everything that exists. But back to the collisions we do understand, sort of. In a traditional black hole-neutron star merger, there are three main outcomes. First, the black hole could simply swallow the neutron star hole, especially if it's much more massive and the neutron star doesn't get close enough to be disrupted. In that case, there's no light, just a clean gravitational wave chirp and then silence. Second, The neutron star could be tidally disrupted before it merges, forming a hot accretion disk of debris around the black hole. That's when we get fireworks, light, heat, and sometimes jets. Third, and much more rarely, the merger could lead to a temporary hypermassive neutron star or magnetar that survives for a few milliseconds before collapsing into a black hole. These short-lived objects could radiate intense magnetic and gravitational energy, potentially explaining some of the strangest transient signals we've seen. But rogue mergers complicate all of that. Because the black hole isn't part of a binary, it may not have a circular orbit. It might crash into the neutron star at a wild angle, or at a speed that's far above what we're used to seeing. That could create strange shockwaves, asymmetric debris fields, or even ejecta that flies off into interstellar space at insane velocities. These high-speed collisions are chaotic and hard to model. They don't fit neatly into our equations. And that's where simulation comes in. Astrophysicists use massive supercomputers to model what happens when a rogue black hole collides with a neutron star. These simulations aren't just pretty animations, they're mathematical reconstructions based on general relativity, quantum physics, nuclear equations of state, and magnetic field dynamics. They help us predict what kind of gravitational waves a rogue merger would produce, how much matter would be ejected, whether or not a disk would form, and what kinds of light signals we should look for. But even the best simulations have limits, especially when the physics involved is still poorly understood. And here's something even wilder. There's growing speculation that rogue black holes might play a role in creating the heavy elements in the universe. We know that kilonovae from neutron star mergers produce elements like gold, platinum, and uranium. But if a rogue black hole merges with a neutron star and causes it to eject a large amount of neutron-rich material, that could be another major source of these elements. In other words, the gold in your wedding ring might have come from one of these cosmic collisions billions of years ago. Not from a star in a quiet binary system, but from a high-speed, chaotic, rogue event in deep space. So when we talk about rogue black holes merging with neutron stars, we're not just talking about rare space events. We're talking about engines of cosmic alchemy, machines that build the periodic table, that shape the evolution of galaxies, that send echoes across the universe for eons. And yet, we've only just begun to understand them. Every new merger detected adds another piece to the puzzle. Every unexplained signal challenges our assumptions. And the more we look, the more we realize just how wild, how unpredictable, and how full of surprises the universe really is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.